USA, Israel, India, and Russia. Proceedings of the present conference, just like the previous ones, are published in proceeding volumes, and the selected papers will be published in the spring section also computer science. According to spring statistics, there were more than 164,000 downloads only during the last year. And in addition, the Publishing House proposed to organize 2 special issues of the respective journals which are included in the first quartile of Web of Science, such as mathematics and census. The organizers of the conference have made every effort for the success of this prestigious international conference. I wish all the participants a successful and fruitful work, and as well health, and health. Thank you very much.
Now, welcome speech to be presented by Director of AMCT Institute РУДН, Professor Samuilov Konstantin Evgenievich.
Thank you very much, Vladimir. It's dear colleagues and friends, ladies and gentlemen, I'm pleased and honored to open the 24th International Conference on Distributed Computer and Communications Networks on behalf of the People's Friendship University of Russia, shortly Rudin University. I'm the Director of Applied Mathematics and Communications Technologies Institutes. It's a great honor indeed, because the level of the conference organizers, of its program committee, and participants who have submitted over 150 papers is extremely high. You all have the conference program at your computers. I will just remind you that the main organizer of the DCCN is the leading Russian institute in the area of control, information technology and computing, Trapeznikov Institute of Control Science. Vladimir Vishnevsky. Let me say a few words. Vladimir is honored scientist of Russian Federation, and our research teams under his and my supervision cooperate for over 25 years. The program committee includes renowned experts and researchers from about 25 countries. They are Austria, Armenia, Bangladesh, Belarus, Belgium, Bulgaria, United Kingdom, Hungary, Germany, Israel, India, Italy, Latvia, Moldova, Mongolia, Poland, Russia, Romania, Slovakia, United States, Ukraine, Finland, France, the Czech Republic, and South Korea. In plenary section, we will hear, let me say, outstanding keynote speakers, and I'm very pleased shortly introduce them to you. Without order, just from the side of the conference. Professor Trivedi, United States, Duke University, Professor Correa, Portugal, University of Lisbon, Professor Levner, Israel, Golan Institute of Technology, Professor Raniti, Italy, Mediterranean University of Reggio Calabria, Professor Strik, Hungary, University of Debrecen, Professor Dharmaraja, Indian Institute of Technology, Delhi. DCCN proceedings will published in book included in Russian Science Citation Index, and selected papers have been reviewed and accepted for publishing in Springer. I strongly believe that the conference brings us together and help us to overcome the pandemic evil. It will contribute to increasing the role of higher education and education system in general in developing Russian science and strengthening the cooperation with the world scientific community. I wish the conference a complete success. Please, Vladimir, the floor is yours.
Thank you very much, Professor Samuilov. And now we are starting the plenary reports. Let me give the floor to the Professor Dharmaraja from Indian Institute of Technology. Professor Dharmaraja, please.
And who is ready? Who knows? Dmitry.
Да, следующий докладчик есть, да.
Okay. Levner is ready because something wrong with India.
Professor from Marty.
Yes. Everything okay.
Oh.
So,
Professor Dharmaraja, please.
please turn on microphone.
Good morning, sir. Good morning, sir.
Okay,
Yes.
okay.
I
Thank you.
listen you.
Yes. And you can turn off our camera. We are waiting a little.
Я думаю, сейчас он включится. Dharmaraja, we waiting you.
Похоже, у него микрофон выключен.
Maharaja, we are waiting for your plenary talk. Are you ready?
Yes, I am ready. But
Please, you can start. You can start.
Oh, I can start now
Yes.
because I thought it is another 10 more minutes.
Okay, nevertheless, if you're ready, please start.
So give 3 minutes.
3 minutes, okay, we are waiting
3
for
minutes,
you.
да.
Vladimir Mironovich, maybe I can ask you to say several words about biography, bio of this respected professor
Most
from
appreciated.
India. Several words.
You're welcome. You're welcome, please.
Yes.
Yes, you can.
Женя, ну мы ждем, так сказать, он попросил 3 минуты там на подключение.
Yes, I see, but you know biography, его биография, несколько строчек, как раз занять эти минуты.
Ну, если
Yes,
бы
you are welcome,
если
Евгений.
бы я мог
Yes.
подробно
Thank
сказать
you.
об этом.
Please
Да.
introduce us.
I believe it is in the program, but not in my hands.
Сказать. Он ищет в интернете.
Okay, you can start.
Профессор Джахамадж.
Yes, sir. I'm ready.
Start, please. We are waiting for your presentation.
Okay. So my introduction, everything is already over.
Yes, we're hearing you well. What else?
Okay. Great. Thank you, Professor. Thank you. Let me share the screen.
Okay. And please, full screen. Okay. Yes. It's okay. You can start. Thank you.
Good day to all. Since it is for local time of Russia, it is around 11 o'clock and 12 o'clock, and for India it is around 2 plus. For different countries, it may be a different time. Instead of saying good morning, good afternoon, and good evening, so I start with my presentation with good day. I'm happy to give a invited talk in this conference. And first of all, I must thank Professor Vishwaneski. And the day this conference work is started, so I come to know that this conference will be there, and so I was very much interested to travel all the way to Russia, but because of this pandemic, I am giving my this invited talk in my office itself. So this is my office. And next, I want to thank Professor A. Krishnamurthy, who is behind this whole my invited talk here. And he is all well-wisher to me the day I joined my PhD program in 1995. And so I'm happy to say that I know Professor A. Krishnamurthy for more than almost 25 years. So thanking these two professors. And next I want to thank my PhD students who involved in this project. That is now she is graduated, Dr. Anupam, and the currently ongoing student Ms. Anisha Agarwal, and my postdoc student Dr. Priyanka Galita. They have given a lot of ideas and what to give, what not to give a presentation, and so on. So they have basically edited this presentation slide. So with this thanking, let me go to my invited talk. And the title is very big. It is a performance analysis of DRX mechanism in LTE networks using Markov modeling. If I want to explain each word, that also will take a minimum 10 to 20 minutes. So let me put it in a very consultated way. I am an expert in probability, in particular applied probability and stochastic modeling. Therefore, I started doing research in wireless networks or cellular networks from 2000 onwards, when I started my postdoc life with Professor under the supervision of Professor Kishore Trivedi from Duke University. He is going to give a talk today evening. That means today's lecture, he is going to give a talk on software engineering and so on. So I learned stochastic modeling from Professor Kishore Trivedi. Then later I was a postdoc under Professor Ataguru Sule Alpha from University of Manitoba, Canada. So I learned how the wireless networks works and how to make a stochastic modeling of that from him. And after I came here as a faculty in IIT Delhi for last 18 years, I have carried out research in 2G networks, then 3G networks, then 4G. Currently, I have a few projects in 5G also. And this research was done during our 4G project sometime in 2 years back. Therefore, many of the concepts which I am going to discuss in this talk, that may be almost with the 4G networks, not related to the 5G networks, but we can always extend the new concepts or new ideas, new architecture which is updated over 5G networks comparing to the 4G networks. You can always extend and easily make it. As far as this presentation is concerned, I have made in the mind 4G networks and the DRX mechanism and all the concepts which are related to the 4G networks. So basically, I'm going to do the Markov modeling, and interest is to study on how one can reduce the energy consumption by keeping quality of service in the mind and keeping all other features in the mind, how one can reduce the energy consumption for the user equipment. So I have divided my talk into this many parts with a brief introduction. I know most of you know all the technical jargons much better than me, because mine is my interest is only a probability person and a mathematics background. The way I understood, I abstracted it some of the concepts into the stochastic modeling. Then I'm going to say what is the DRX mechanism in user equipment and some of the main important features which I'm going to explain. And then I'm going to say how one can make a stochastic model, that is what is a model description of it. After that, I'm going to introduce what is a performance analysis for that. And finally, since these results are more complicated in the sense, so I'm going to introduce some of the numerical illustration or sensitivity analysis for that. With that, let me complete my talk. I planned my talk roughly for 40 minutes, and since I have started some 15 minutes earlier, therefore I will make sure that I will finish my talk much earlier, as well as I will give some time for audience to ask the questions, so that I will enjoy what are all the things I have explained to them and what are all the mistakes I have done, and how I can improve my talk also I will understand at the end of the questionnaire. These are all not the important jargons. There are many more, but at least I have just made a one slide. Without stochastic process, one cannot make an analytical model for any performance analysis of wireless networks. So this is the way I learned from Professor Kishore Trivedi. Understand the dynamics of the system, extract it, then identify what is the underlying stochastic process for that, map it, then you try to get the closed form solution if possible. If not, try to get the numerical solution, or sometimes you go for finding the numerical solution via software tools, or you can go for the simulation also. So there are many ways one can achieve the quantitative evaluation of underlying model. So for that you need a stochastic process. So I'm not going to teach what is stochastic process and all. So we are going to use the stochastic process in the stochastic modeling to get the results. And not only mobile communication, we are going to use many more jargons, wireless networks, cellular networks, and there are many more architecture, and how the base station works, and how the whole network architecture is planned, and what are all the redundancies used to take care of the quality of service, and so on. So at least minimum things are needed to make the stochastic model. Then the next one is LTEA. That is also one of the important. Yes, please. Is the screen is share? Are you able to see the screen? Ah, okay. 1 minute. Let me try to get the same screen. Are you able to see the screen now?
Yes.
Yeah. Thank you. So when we do the stochastic modeling, this type of failures also we consider into the consideration. That means you never know when the connection is there, what are all the components is giving a trouble to have a end-to-end communication. So that is also important. So those things we study under the title called availability analysis. So here I am going to concentrate on the performance analysis. But if you see some of my research publications, we have done, we have carried out a performance analysis, availability analysis, surveyability analysis, and so on. Now I am coming to the LTEA. LTEA. This is a very important standard which will enhance the power consumption in the 5G networks. I'm not going deep into all the jargons because I'm not the expert, but the way I understood, I abstract it and I make use in the model. The next important jargon is user equipment. this particular model is related to the user equipment, and the same modeling approach can be extended to the base station, and then it is possible to combine the stochastic modeling, both user equipment and base station. Not only one base station, you can think of considering many base station put together, you can make a composite model also. So I have done those many things in the other research work, not for this particular energy issues. But what I'm saying is I made a stochastic model in this talk only for user equipment, but currently we are working on the similar analysis for the base station, and keeping the energy in the issue, we are considering the base station also, but this is for only user equipment. Next important concept is DRX in short. This is also very important concept related to the power consumption. And DRX also here we are considering for only user equipment. The same concept is used in the base station also to reduce the power consumption. So here we have used only for the user equipment. One minute. Yes. Which motivates to do research in this area? The way I started my research career in 2000, I started with the 2G networks by keeping performance as the important issue. How one can reduce the call blocking probability, call dropping probability. Suppose you have a handoff calls or new calls. If you have a given bandwidth, how we can configure the base station or one cell such a way that you can reduce the call blocking or call dropping probabilities, or what is the optimal channel has to be allotted, or what is the call admission policy has to be adopted so that you can reduce the call blocking and call dropping probabilities. But those days the bandwidth is the issue. How one can optimally use the bandwidth. Those days only voice calls are there. So the issue is suppose you have a only voice calls, only that is the only service. How one can configure the base station so that your quality of service or quality of service can be guaranteed. Whereas over the period, the services are increased over the period of time with the data and video and so many things we have. Now there are many more real-time applications than the non-real-time applications. Therefore, the issue is both bandwidth as well as the energy is the issue. But bandwidth is taken care with the nice technology. Nowadays, the bandwidth is not the big issue comparing to the energy. So the question is how one can minimize your energy consumption for a given configuration, or the reverse or inverse problem is what is the configuration you should make it for this particular network such a way that your power consumption may be less. If you go for probabilistically, then expected power consumption has to be minimized. That means what is the configuration so that you can reach this goal. Of course, you should keep it quality of service also in the picture. That means it's a issue. If you keep the system is completely off, then there is no power consumption. But your quality of service or the throughput will be almost zero. That means you should make sure that the given throughput or given quality of service is taken care. At the same time, how to minimize the energy consumption. So the question is how to configure the system, or what is the optimal parameters, because certain parameters are with our hand. There are certain parameter values that is dynamics with respect to the users that we cannot control. For example, the arrival request, the packet arrival, that is not in your control. So at least based on the back history, you can estimate what could be the values of the parameter and what is the distribution it matches with the current scenario. You can include in your model, but you cannot control the values of the parameter. Similarly, the transmission. Maybe you can little bit change the transmission rate and so on based on how fast you have a system, but you cannot do much more with the service rate. You can minimize the delay, but you cannot do much on some parameter values. So the question is how one can configure the system. That means whatever in your hand, for example, you can switch off some components. You can wait for some more time before wake up, because when you wake up, then most of the components will be up, then those components will be using the energy. So you can strategically identify these components can be switched off because of these services are not used at this much duration. Then I can wait for some more request, such a request comes, then I can make some components up or some components wake up. Therefore, the energy consumption will be there. So wherever I can identify, I can make a strategy or I can make a policy such a way that I can reduce the power consumption. So this is the objective in this problem. And please remember that it is a very early studies, whereas the current technology and the current concepts are much more than what I have adopted in this paper. Right? So therefore, energy is important. Whatever the way I want to convey, I have conveyed how much energy is important in this current scenario. And more than that, now, other than the usual energy, now the question is how one can use the solar energy for the green evaluation. How one can use the solar energy so that you can minimize the usual power and the energy consumption also. Therefore, even though we have not attempted any solar energy concepts in this paper, but currently we are working on it. But keeping all those things in the mind, we are saying the energy is a very important issue other than the performance which we usually study in those days. Now the energy is important. That's what I want to convey. Now I am coming to the important slide, how the DRX mechanism works. This is again a very abstract diagram. The way I want it for stochastic modeling, I have made the width for something, I have made a width for something else in a different way. But there are some durations are in seconds, some durations are milliseconds. So therefore, there is a possibility of scaling of the duration in these diagram mistakes, but still you think of it's for the stochastic modeling. So some durations are seconds, some durations are milliseconds. That means whenever the packets arrived, the system starts servicing, giving the transmission and so on, then we call it as a busy period. Whenever there is no packet, most of the components goes to off state and make it power is not going to be used at all. That is called the power saving state. So the system goes to the sleep period. The user equipment goes to sleep period. It could be a different sleep that we are going to say it later. So that time the system is power saving. It's saving the power. Whereas when the system is transmitting the packets and so on, then that could be call it as a busy period, and that time the power consumption is going on over the time. The rate in which the components are used, accordingly the power consumption will be there. And in between sometime, there is a very small amount of time the system is waiting for the packet to come. If there is a packet, then immediately it starts servicing or it starts transmitting. Therefore, the service or transmission both are one and the same. Because I am going to map the whole mechanism with the queuing model. Therefore, I will map with the all queuing jargons over the period of time. So the way I made the earlier slide, there are some sleep period going to be called it as a short sleep, or that is called the short DRX cycle, and something are called the long DRX cycle. Yes. So the meaning of short and long means the duration is short, then it is called the short DRX. I think somebody made the on. They can mute so that. noise can be avoided. Yeah, it's fine. Thank you. So what I am saying is when the system is in any one of the sleep period, one is called the short and the other one is a long, the duration is going to be more for the long DRX cycle, and the duration of sleep that is going to be shorter, that is going to be the shorter. And there are number of short DRX cycle, that means the number of times the system goes to the short DRX cycle. After waking up, if there is no packet, then again it goes to the sleep. Wake up, sees there is no packet, then again goes for the short sleep. So the number of short sleep, that's also random variable. You can identify what is the number to make so that you can have a good throughput as well as minimum power consumption. Similarly, the long DRX cycle also, you can have how many times you can have a long DRX cycle sleep time. That also can be tuned based on the constraints. We are not the only person started mapping DRX mechanism of UE with the stochastic modeling. Already the people started working on it, and now I am going to introduce the professor who introduced energy into my area of research, that is Professor B.D. Choi. Many of us knowing this professor from uh, South Korea, Seoul, and he is a well-known person. He is a mathematician and moved to the Department of Electrical Engineering, and he had a lot of projects, and some of the projects he handled the energy issues for the wireless networks. And once he gave a talk in some conference in Coimbatore in India, I was just listening his talk. So that motivated me to understand other than the blocking probability and dropping probability of wireless networks, one can work on the energy issues for the wireless networks. So from his papers, I started picking up. Then I visited his place and he came to IIT Delhi 1 or 2 times. And because of so many interactions, I understood how the wireless networks works, keeping energy in the important issue. Then I started research in this area. So at this point, I am thanking Professor B.D. Choi introducing me into the research of energy issues. So already there are many more authors. They have carried out the stochastic modeling of wireless networks in these areas. But what we are going to do, we are going to improve those model. They made it very easy of discrete time Markov chain with the few number of states. And for some people, they have introduced only MG1Q or with vacation or without vacation and so on. But whereas we have improved whatever the existing literature at that time, we improved it to make it better, such a way that we are able to get the better minimum power consumption as well as the other constraints, whatever I said earlier. Yes. So the main contribution which we made it in those days, that is we mapped this DRX mechanism in UE with the batch arrival, general service, single server with the vacation, as well as N policy and some number of fixed number of vacations. All these words are important because you can have a request can be a batch or it could be 1 by 1. So applying or mapping the existing problem with the batch arrival, that is a very important thing, and identifying what is the correct distribution which matches to this research we have carried out. And instead of service follows exponential distribution, we have made it with the general distribution. Therefore, any distribution which has the at least some finite moments can be applied, and you can map with that and get the results. And the vacation queue is very important because the system you consider as the going for service or going to the sleep and coming back, that can be considered as a vacation. And now the question is, when it will be come back, if there is no packet, whether it will go for another vacation or it will continue sleeping till at most some number of packets or some number of customers entering into the system. So that is called the N policy. So we introduce a N policy. That means if at least N customers in the system, then the sleeping server can come back to the system. Otherwise he will continue the sleep. So the N is a positive integer. And since we are introducing N, we can find the optimal N also. Therefore, we have identified what is the optimal value of N so that the constraints are satisfied. Similarly, how many vacations one can do? Whether we can have 2-3 vacations or 5 vacations, or how many vacations we can do, that also we can do the optimization problem. But everything is related to the historical data. In this research, we have assumed that parameter values or parameter distribution and so on, if somebody is good in statistical inference, you can get the actual data, then you can go for estimating those parameters. Then you can identify what is the correct distribution which matches with the data. Then you can plug in the distribution also. Whereas here in this work we have not concentrated on any statistical inference side, but somebody is needed, somebody is interested to work on one particular base station or one particular tower or one particular cell, then they can carry it out with the historical data also. Finally, we have validated our whatever the findings. We are using a numerical illustration by MATLAB code and verifying our results. Whereas we have not done with the simulation comparison and so on, because we mapped nicely the queuing model, and we are just giving a sensitivity analysis by varying the number n and varying number of vacations. Therefore, we have done more sensitivity analysis. Therefore, we don't need the discrete event simulation to compare our analytical results. Now I am coming to the model description. This is also a very important slide. In the sense, we keep x-axis time, and if you see y-axis, we keep 4 levels, and each level talk about the different things. The top level says how many packets in the system over the time. So that dynamics, you can see it in the top one floor. Top floor, you can see how many packets at any time. Therefore, accordingly, the decision is taken. Suppose the number of packets is waiting in the system is more than n, then immediately the sleeping server will come back and start the service. He would have gone for sleep when no packet in the system, but when he is going to come back after making so many sleeps continuously, some finite number of sleeps, there is a possibility he may sleep for some more time because of minimum n packets are not arrived, and we can find the optimal n also. So that is a one information we are giving in the one top layer. And if you come to the next level from the top, that is a vacation period. So based on the service, the system will be under service, or it will go to the vacation. If no packets in the system, then it goes to the vacation period. So each blocks are going to be a different DRX cycle, different vacation period the system is taking, and either it is busy or idle or vacation and so on. And in between also it takes some time to switch over from one period to another period. Those times are negligible, but still for the visibility we are making widen. We didn't bother about the actual scaling, but actually some things are seconds and some things are milliseconds. So don't bother about the scaling issue. Next is the DRX cycle. That means sometime the system is in the short DRX cycle. That means very less time it goes for the sleep and come back. So that is also some K1 number of times the system goes for the short DRX cycle. Still there is no packet in the system, then it goes for the long sleep, long DRX cycle. There also it takes some number of times it goes for the long DRX cycle. If no packets coming to the system, then it will keep on sleeping, or if there is no n packets waiting in the system, then it will continue the long sleep before coming back to the original state of active state. And the difference, all those things related to the energy, because that is our motive, objective. The energy is used when the system is active. That means while transmitting. If it goes to the short DRX cycle or long DRX cycle, there is no energy consumed. Therefore, it is called the power saving state. And in the power active state also, based on the service and based on the which one service is going on, your equipment, the power consumption cost also will vary. That we are going to discuss later. But early in this model, we are keeping the cost is same. But when the different services you are providing within the user equipment, the mobile device itself, some component will be used, some component will be not used, and so on. But whereas here we have made it a very easy model, whereas you can complicate the model with cost or energy for different subcomponent at over the period of power active state can be different. Therefore, when you get the expected power consumption can be calculated. That I am going to do little later, but what I am saying is at the lowest level we are discussing about the energy consumption based on the system is active or system is non-active. Accordingly, your energy is either consumed or not consumed. Next, here we are coming to the stochastic modeling. Actually, this is not a Markov chain, or this is not the continuous time Markov chain because of few factors. The service time is not exponential distribution, and the vacation period, that is the short DRX cycle as well as the long DRX cycle, both are non-exponential distribution. Whereas the packet arrival, still we keep it as the arrival follows a Poisson process, or inter-arrival follows independent exponential distribution. Still we are keeping the batch arrival. But all this complication makes over the time, the Markov property won't be satisfied at all time points. You see the Markov chain. I don't want to read out whatever the state definition, the Markov chain, sorry, in the stochastic process. In this stochastic process, you may not have a Markov property satisfied at all time points because of many non-exponential dynamics going on to make the system into the different state. You can observe whenever something happens at some time epochs, the Markov property may be satisfied. One can identify, if you recall your MG1, if you recall your knowledge in the MG1Q, or if you recall your knowledge in GM1Q, you will identify in the MG1Q, whenever the departure epochs, those time points, the Markov property will be satisfied, not all time. That means the stochastic process at any time, that is not satisfying the Markov property, whereas at the departure epochs, if you observe the system, that means that is going to be a discrete time stochastic process that will satisfy the Markov property. Therefore, that becomes the discrete time Markov chain. That means the actual stochastic process is not a Markov process in the continuous time. Whereas if you observe the system at the departure epochs for the MG1Q, then that follows the Markov property. Therefore, the embedded stochastic process, that is the discrete time Markov chain. The continuous time stochastic process is not a Markov process. Whereas if you collect the stochastic process at a few time points, those time points are called the regeneration time points. That means the time points in which the Markov property is satisfied, we call it as a regeneration time points. So if you observe the system over the regeneration time points, for MG1 queue. In this model, it is a batch arrival, MG1, occasion queue with the n policy and at most a finite number of occasions. Therefore, in this model, if you observe the system at the end of sleep times, that means either short DRX cycle or long DRX cycle whenever it ends at that time points, that is a T plus superscript plus. At those time points, you will have a Markov property will be satisfied. Similarly, whenever the service is completed, because the service is happening during the system is active, and the system is not active, that means when the DRX cycle is going on. So at the end of every end of DRX cycle ends, then the Markov property will be satisfied. Similarly, whenever the packet transmission is over, that time the Markov property will be satisfied. Whereas in between any two subsequent DRX cycle, there may be number of packets will be added into the system. Therefore, the system go to the different states with respect to the number of packets, but that won't satisfy the memoryless property. Whereas the service epochs, service completed time epochs, or at the end of a short DRX cycle ends, or at the end of long DRX cycle ends, the Markov property will be satisfied. Therefore, the embedded one in this bivariate stochastic process becomes a Markov chain. Once you have a discrete time Markov chain, you can get the steady state or stationary property. That is same as the limiting distribution, because it satisfies the ergodic property. That is irreducible, positive recurrent, and irreducible, aperiodic, and positive recurrent. All those three properties will be satisfied by the embedded Markov chain. Therefore, whether you get the steady state probability or limiting probability or stationary distribution or equilibrium distribution, all are going to be one and the same, because the system is ergodic. Since it is ergodic, one can do the nicely discrete event simulation also, and you can get the result and compare. Whereas here, because ergodic property is satisfied, we got the steady state probability nicely, and because of that, we make the steady state probability being in the different states, because it's a bivariate stochastic process. Identifying embedded Markov chain and drawing the states will be very difficult. Therefore, you can identify which are all the states are going to be inactive, which are all the BC period, which are all the short DRX cycle, which are all the long DRX cycle. You can identify those states, and you can identify the limiting probabilities or the stationary distribution. And once you have the steady state probability, our interest is how to find the power consumption. So attach the rewards. The rewards is nothing but how much power is consumed whenever system is in these states. So you multiply those power values as a rewards and multiply with the state probabilities and sum it up. That is basically expected reward. This also I learned it from Professor Kishore Trivedi. Suppose you have a state probabilities, whatever the measures you want. Suppose you want the availability measures. You can attach the reward as the availability values to those as the rewards for those states, and multiply the probability and sum it up. That is going to be the expected reward. So here the expected reward is nothing but the expected power consumption. That is going to be a function of n and k, because you vary the n, you will get the different result. You vary the number of sleeps, then also you will get the different values. So we are keeping n and k2. K2 is the number of total number of both short and long DRX cycles, sleep times. So we are making these two are the variables, and we are going to identify what is the minimum n as well as minimum K2, so that you can have the minimum power consumption. So that is the objective of the problem. So for that, we have made the expected reward function And I'm not going to read out all the explanation. It is there in my paper also. And since it is a two variables, therefore you should nicely apply first one variable. You have to fix it and identify what is the minimum value. Then you keep on increasing the different n with respect to n. What is a K2? So you can identify what is the minimum n as well as the minimum K2 such a way that you can minimum have a energy consumption by doing these algorithms again and again, so that you can identify what is the minimum number of packets you have to wait so that you can wake up from the long sleep. We have done the sensitivity analysis in the sense we vary the parameter values because for example in one particular city the empirical data will give the values to the parameter within some range. Some other city the values may be different. Therefore, you cannot assume only one value to the parameter values. Better you do the sensitivity analysis for whole range of parameter values. Then you identify what are all the results you are going to, what are all the performance measures, which here the performance measure is power. So what is the power, expected power consumption by keep varying the arrival rate, that's a arrival rate of the packets. And you can still do the number of packets to be weighted at n policy, that also you can vary. So you can make out how much n we should go for this particular range. So based on the different information in the actual data, you can identify what is the n to be implemented in your system so that you can get the minimum energy consumed. Not only arrival rate, you can identify, sometimes you can feel, oh, okay, so I am getting a trouble, I can more transmit very fast so that I can get the things. So that also you can vary by varying the service rate. That means how fast I should do the service so that I can change, I can get the results in with respect to the service rate also. Similarly, we have what is expected. So whatever the measures we can able to find out with respect to the different parameter settings, that is nothing but the sensitivity analysis. So we have done the sensitivity analysis based on different range of parameter values so that you can get the feel. So for this research, you don't need the comparison of simulation because you are not fixing anything. You are varying all the parameter values and you have feel what is the range in which what is the results you are going to get. Everything is in this visible way. Therefore, there is no need of comparison. Similarly, the expected length of inactive timer. These are all the n we have fixed it. But even though you feel like these n's are very small, how I can make a wireless networks with the number of packets is 20 and 40. So this is just a sample. Therefore, you can scale it accordingly because whatever the measures which we are getting with respect to that scale. So you can always, because the MATLAB is capable of doing some range. After that, MATLAB won't give the results. Therefore, we make a very small number. We get the difference of the values. But in the actual system, instead of MATLAB, you can always go for the better computational parallel computing, or you can have a high-end high-end computing methodology to get the result. Even if you have a largeness problem, that means you have a system with big numbers as the parameter values, which is not possible with the MATLAB or not possible with the parallel computing and so on. You can go for identifying what is the equivalent less number of a system. So that means there is a how to avoid the largeness, how one can take care of largeness problem. That means you can identify equivalent simple number of small number of states model. From there you can get the results. So this also I learned it from Professor Kishore Trivedi. There are many more techniques are available based on the need. Sometimes the students ask, can I use this modeling methodology? Can I use this technique? Can I use this algorithm. There is no fixed algorithm, there is no fixed methodology, or there is no fixed model has to be always use it for this. Based on the need, based on the objective, based on what is the information which is available with you becomes the input, and what is the objective or what you want it, that is going to be output, and what is the model which suits to for this input, for to get this output, you have to identify what is the closest model or closest techniques and so on. So this is what I learned it as a stochastic modeling in my research for past more than 15 years. Yeah, here also I have made some more graphs. Again, it is a sensitivity analysis, not more than that. Yeah, finally, how one can get the power, expected power consumption with respect to the values which we are able to get it for optimal N and K2. By varying N and K2 also, how much you are going to get the different results by varying the other parameter values. I'm not able to recall how to get these parameter values. I completely forgot now. But there are various, can fix the parameter values for something, some parameters, then you can vary and so on, because it involves more than 5 parameter values. So at any time we fix some parameters and we vary few other parameters, those are all critical parameters. Then always we keep one axis is for the performance measure. Even though there are many more literature and papers on it, I have listed a few things. And the first one is our paper, which is published in 2020. So whatever I have presented today, that is the paper appeared in Annals of Telecommunication. And whatever I was telling extra information, which is at present work on 5G networks, as well as work on same concept in base station, and whatever I have carried out over the time on performance evaluation and all those things I have said. So those who are interested in those topics, you can always go to my homepage, and in there you can find the publication page and you can identify the research article and you can understand. These are all the very important papers, therefore I have listed out for this particular research work. But in general, for stochastic modeling, the very good reference is go to the website of Professor Kishore Trivedi, and you will get different stochastic modeling based on the input as well as based on the objective and based on the problem which you have it in your mind. You will identify different stochastic methods, starting from discrete time Markov chain, continuous time Markov chain, semi-Markov process, Markov regenerative process, non-homogeneous Markov regenerative process. I have some work on non-homogeneous Markov process, non-homogeneous Markov regenerative process also. Other than that, reliability block diagram, fault tree, we can use those things also to do the similar stochastic modeling, and we can do it via stochastic Petrinet also. Professor Kishore Trivedi has a software to analyze the different dynamic system by making a stochastic Petrinet and getting the results. So with this, let me complete my talk. Once again, thanks to Professor Vishwanesh Ki and Professor A. Krishnamurthy giving this opportunity to me. And thanks to my research scholars who helped me to prepare this slide. And whatever the mistakes I am making, that may be due to the memory loss property. I would have forgot some concepts, therefore I would have made a mistake. So whatever the mistakes you tell me, I will correct it. And those who are interested to know many more other research in my this stochastic modeling topic, you can always go to my website and read those papers. With this, let me complete my talk. Thank you.
Включи, пожалуйста. Thank you very much, Professor Shharmaraja. A question, please. If you have any question, please raise your hand. Udo Krieger. Professor Ugo Krieger.
Yeah, this is Udo Krieger speaking from the UNESCO Heritage City of Bamberg, Germany, in Bavaria. Thank you for the talk. Have you validated this kind of model in terms of a simulation, for instance, Simul LTE, sir?
Professor, could you please repeat the question again?
Have you validated the model by Simul LTE, the Omnet++ simulator of the LTE testbed? Because this is the most important for applied sciences validation.
It's a good question. There are many ways one can validate the stochastic modeling. And one of the important things which you have said, the simulation approach, because the problem related on wireless networks, there are many more standards are already tested and validated with the simulation. Therefore, one should do the validation via simulation. But my knowledge is almost zero in the simulation, and I always do validation by sensitivity analysis or the existing or earlier literature work, not by simulation. Still, I have done one or two simulation validation, but that is also the way, it is not the way you said. So I have not done simulation validation, but under my supervision, I don't have very good students who are good in simulation as well as understanding the stochastic modeling. Therefore, sorry for that, and I have not done it. Thank you.
Thanks. Professor Levin, please.
Yes, I have a question. First, thank you, Professor, for very interesting talk. And my question, which other methods can be useful for saving energy in your problem? For example, I remember some early papers on using integer programming or some other operation research methods, not only Markov chains. What is your opinion about other methods?
It is a good question again. We are happy with the Markov modeling always, but actually the system it behaves, it is not having a Markov property at all. So we make the assumption it has the Markov property, therefore we can make the Markov modeling, therefore we can get the results nicely. But there are many more non-Markovian models are available in the literature. For example, you can apply the renewal theory. That means you can apply the simple concept of renewals takes place over the period of times, and you can apply the non-homogeneous concept. You can apply the non-stationarity concept. So the Markov property is a very, very easy concept to get the closed form solution, but actually one should go for a non-Markovian setup and get the solution. It is possible with the discrete event simulation. Therefore, we always compare or we try to compare the discrete event simulation, which is a non-Markovian setup, with the Markovian setup of analytical model. So the answer to your question is the non-Markovian things comes with the discrete event simulation or with the non-homogeneous renewal theory and more complicated stochastic processes.
Another question.
Please.
No question. Thank you very much, Professor Tsorkamat. I am very glad to see you. Thanks. Now I invite Professor Evgeny Levner from Holon Institute of Technology, Israel.
Okay, thank you. I need several minutes to put my to my slides. Please give me 2 or 3 minutes.
Okay. So thank you, Professor. I am leaving the meeting.
Bye-bye.
Thank you. Bye.
Thanks.
Okay. Hello. Something not good with my computer. You see? Okay.
You, Женя.
Okay, hello to everyone. There is a horrible echo.
Sorry.
I'm sorry for this echo.
Don't share your screen.
How can we delete this echo, please?
Switch off the loudspeaker and then you will have no echo. It's a feedback.
Maybe I should download again because this echo is horrible. Let me download once more.
Okay. Так, теперь мы не слышим.
Евгений, попробуйте отключить или сделать потише звук на компьютере. Тогда, возможно, пропадет F.
Либо, может быть, есть возможность использовать гарнитуру. Наушники.
Вы меня видите? Вы меня слышите?
Слышим.
Окей. Тогда я начинаю. Как
Да.
раз время без 4 минут час. Это мое время.
Евгений, только
Окей.
не пошарили экран.
Скажите, пожалуйста, вы видите экран?
Нет, нет.
Нет, экран пока не видим.
А сейчас?
Нет, нет, вам надо поделить.
Я должен... Сейчас. Я должен, наверное, сделать share. Минуту. Сейчас, минутку. Can display content. Some problem in my screen. I try to open share screen.
Yeah.
Share screen. But no share screen.
Ой. We see your screen. No. Yeah, we see your screen.
Мы видим презентацию, спасибо.
Да, сейчас видна презентация, да?
Сейчас, но это, к сожалению, это не то. Сейчас, минутку, я найду то, что надо. Это не то. Сейчас я должен закрыть это. Сейчас. Вот это. Скажите, сейчас есть презентация на экране?
У нас выключен микрофон, да?
Да. Что делать? Hello, микрофон. У меня микрофон включен, но вы меня не слышите.
Мы слышим, но не видим презентацию, к сожалению.
Сейчас. Вот сейчас вы видите презентацию на экране?
Пока нет.
Так, плохо.
Вам еще раз нужно поделиться.
Я это закрою. Так. Я потерял экран. Как мне восстановить экран конференции? экран конференции, где он? Он пропал с экрана.
Либо в приложении Teams, либо в браузере. Смотря как вы подключены.
Где он может быть? Нет. Черт. Нет. 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 Микрофон. Нет. А сейчас вы видите экран? Сейчас виден экран?
Нет, сейчас не виден. У вас в Teams просто надо вот share сделать еще раз.
Еще раз сделать share, окей. Я понял. Проблема в share. Сейчас, одну секунду. Так, я вот это закрываю. Сейчас это я закрываю. Но у меня пропал экран конференции. Куда, как мне его вытащить?
Ну, у вас где-то должно быть открыто приложение быть через, я не знаю, панель найдите.
Нет. Нет.
Ну, скажи, либо приложение, либо в браузере.
Я сказал, либо в браузере у вас вкладка, смотря как вы подключались, просто я не знаю. Вы через браузер или через приложение?
Сейчас, одну минуту. Сейчас. Как мне выйти? Я хочу выйти. Как мне выйти из этого сеанса?
Ну, только открыв приложение, либо окно в браузере, через которое вы подключены.
Dear colleagues, we are taking a 10 minutes technical break because at the side of professional next speaker, there are some problems with the environment. So 10 minutes break.
Так. Вы меня слышите? Хорошо слышите?
Да.
Хорошо. Вот я включаю еще раз ставим этот самый скрин. Вот я включаю свою презентацию. Сейчас вы видите... Нет, это не то. Сейчас. Скажите, пожалуйста, вы видите сейчас что-нибудь на экране?
К сожалению, нет.
Алло? Опять эхо. Скажите, вы видите экран?
Нет.
Нет.
Нет, не видим.
Ну, я еще раз поднимусь. Я еще раз поднимусь.
Попробуйте еще раз поделиться контентом. Либо, может быть, вы пришлете свою презентацию, мы будем переключать ваши слайды.
О, тоже.
Ну, это мне не нужно. Это фигня какая-то.
Профессор Левнер, не могли бы вы прислать свою презентацию на почту либо Владимира Ивановича, либо оргкомитета?
Professor Levner, we begin.
Окей, я вижу картинку. Вы меня слышите?
Да, хорошо слышим, да.
Окей, разрешите я начну. Уважаемый председатель, уважаемый Владимир Миронович, уважаемые члены оргкомитета, уважаемые слушатели и члены конференции, участники, participants. Okay, now English.
По-английски.
Okay, the chairman of this conference, the member of organizing committee, the participants, good morning, good day. I don't know what hour now in your country. I present a survey devoted to recent advances in scheduling theory. Scheduling theory, like a queuing theory, it is a very well-known area in operation research, in applied mathematics, in optimization theory, and it is interesting that in recent years there are some new ideas, new approaches, new methods in scheduling theory, which can be very useful for application in communication system. In our talk, please next slide. Okay, in this slide, you can see that we selected in this survey, to devote this survey to 4 main parts which appeared in scheduling theory in recent years. First of all, it is multi-agent scheduling. Second chapter, it is integrating scheduling theory and queuing theory, question on the borders and the mutual influence of scheduling and queuing problems. Then the third chapter is devoted to approximation algorithms with performance guarantees. Mainly we will talk about Christophidis-Serdyukov algorithm for traveling salesman problem and so-called almost optimal scheduling algorithm. And the next and final part of our survey will be devoted to application of scheduling models and scheduling methods for new area for drones. It is robots, it is flying robots, it is what is called flying unmanned vehicles, drones, and how they can be used in communication networks in recent years. Please, next slide. Next slide, please. Okay, scheduling theory appeared about 60 years ago. Of course, people use scheduling and planning much earlier, but systematic study and computer-aided methods and algorithms for scheduling problem were initiated by papers by Seymour Johnson, Richard Bellman, Smith. This is papers of 1954, 56, and then appeared a lot of papers, a lot of monographs. Among them, we mention monograph by Vyacheslav Sergeyevich Tanaev, one of the first, which was first in Russian and then in English, and several other monographs and textbooks, which you can see on this slide. Recent and latest survey by Lenstra, Jan Karl Lenstra and David Schmois include classical and new results. It is very useful. In our survey, we do not go into much of mathematical details. Our aim to give a wide picture of new direction and new approaches and how can be used for robots and for communication system. Now, please, next slide. We start our survey with a topic of multi-agent scheduling. What does it mean, multi-agent scheduling? It is a part, it is a branch of scheduling theory where there is not a single criteria. It is multiple agent. Usually this is human agent which are responsible for different criteria. And what is the difference with other scheduling problems? First of all, and main difference, it is the presence of very many agents and many criteria, and every agent is usually it is a human agent. Usually, it is he or she, they are responsible for their own criteria, and in contrast with what is known for classical scheduling problem, this agent can cooperate, they can conflict with each other, they can organize groups and association, they can struggle with each other, they can express their emotion like a mathematical model of regret, mathematical models of losses, mathematical models of psychological and other feeling and other losses. And this is, in fact, the main difference between a classical scheduling problem and multi-agent scheduling problems. Next slide, please. We give reference to several surveys, which you can find both on this slide, and also, of course, it can be found in more detail in the paper version of this survey. In the published version, you can find survey by Cohen, survey by Alessandra Agnetis, other people. Now, I can only mention that there appeared a new area in game theory, which is exactly on the border of classical game theory and classical scheduling theory. And this branch, these games are called job scheduling games. And it is absolutely new area which combine ideas of game theory, scheduling theory, and different psychological and human aspects of these problems. Next slide, please. Now I have some time to go into cooperation and integration between scheduling theory and queuing theory. In this chapter of our survey, we mentioned that scheduling usually, what is scheduling problem? It is usually parts, machines, processors, and robots. which can you see on this picture on the left side on the slide. On the right side, you can see some vision, some image of queuing theory, where there is one or several service station, and of course there is a queue. Of course, there are many different features in these two types of problems. First of all, problems are different. Description, criteria, objects are different in this problem. Also, methods are different. If in scheduling theory, the main attention usually paid to polynomial, effective, good algorithms which are solved by modern computers. Complexity aspect, this is one of the most popular question in modern scheduling theory. In queuing theory, at the same time, usually authors, researchers use classical method of analysis of queuing lines, for example, Markov chains and other ways of using analysis of different parts of this queuing. The analysis of waits and climb, analysis of service times, analysis of all characteristics, and the main attention is paid to optimizing of lines and all different components of the queuing line. Next slide, please. What is interesting during the early years of queuing theory and scheduling theory, it was 50 years ago, Richard Bellman noticed that there is many similar features, but there are many similarities between queuing theory and scheduling theory. And this notice, these ideas was, of course, extended, continued, and analyzed in more detail in recent years. Please, next slide. In this slide, we want to say that there are many examples when we can observe integration and mutual influence between scheduling problem and queuing theory. And in the paper version of the survey, you can find in detail 3 classical and bright examples. The authors of these examples are Richard Bellman, Michael Pineda, and Daria Terika from Canada. Next slide, please. Here we cite citation from Richard Bellman from his famous paper written many years ago in 1956, where he says, you can read what is written here. The main idea is that if we will take scheduling problem, if we fix an order of if we fix order of tasks, if we compare distribution of waiting times, which is stochastic in scheduling, stochastic in queuing theory, and fixed and not stochastic, deterministic in scheduling problems, you can see that there are many similar features. The same, please, next slide. The same idea, the same notion was developed and extended in several papers by Michael Pineda, who wrote several bright papers and a very famous book on scheduling theory. And here you see 4 first examples of classical scheduling problem, which he successfully solves and solved very efficiently, very in very good complexity and very good results. This is problem of expected weighted sum of job completion times when there is a single machine. The same problem when there are several parallel machines working in parallel, and also similar problem when he was interested not in a total time, but in a number of late jobs. But in all these problems, all parameters were stochastic. He introduced exponential distribution. And what is interesting, he proved that problems which were solved efficiently and in polynomial time in deterministic version, the same results or similar results about efficient solution, efficient algorithm, but in the case of exponential and other distribution, in fact, it was he considered version of queuing problems. Several versions of queuing problems were solved by methods of scheduling theory and also classical queuing methods like Markov chains. And he received very positive, very attractive results. What is most interesting, our notion in this area, there are problems which are not solvable in scheduling theory. They are hard. They are NP hard. This is a notion in complexity theory. They are NP complete and not solvable in our time. But when we add exponential or some other distribution, surprisingly enough, the problem becomes easy. It becomes treatable. It becomes solvable in polynomial time. This is one of the most interesting on the border of scheduling and queuing. Next slide, please. In recent year, we discovered several papers. In fact, it is a series, it is a cycle of several papers by Daria Terikov and her co-authors from Toronto University. And these authors noted that if they use concept from queuing theory, namely the concept of stability and concept of periodicity, then some simple and also some complicated scheduling problem, they obtain some good solution. They obtain efficient algorithms. And what was especially interesting and maybe unexpected and surprising, algorithm which were constructed by Terikov and all co-authors as a hybrid combination, integration of ideas from scheduling and ideas from queuing theory. And this algorithm turns out that in their mixture, in their integration, they work better than very well-known separate queuing algorithms or scheduling algorithm. They prove this fact for several simple scheduling problems like flow shop and job shop. But what is even more interesting, they made some empirical and computational experiments and discovered that the same fact is not proved, but it is not proved theoretically, but in practice turned out that hybrid algorithms, mixture of queuing ideas and scheduling ideas, these mixed algorithms in practice they work better than separate algorithm and outperforms in complexity, in running time, in quality, in accuracy, all other algorithms which are separately known in scheduling theory or queuing theory. This is very interesting and open area for future research. Next slide, please. Our next chapter in our survey, our third chapter, devoted to so-called approximation algorithm with performance guarantees. When we meet in scheduling theory or in computer science or in practice difficult, hard problems which are unsolvable by exact methods, we try to find good approximation algorithm, but most interesting to find performance guarantee. Not just to say that this solution is approximate, but what is estimation for error, for inaccuracy of this approximation algorithm. And one classical algorithm in this area was obtained for traveling salesman problem. It is classical problem which is known in computer science, in optimization, in scheduling theory. On this picture you see that there is a map of cities, of nodes, and the problem is what is the shortest possible close route which visit each city exactly once, returns to the original city, and it is shortest, it is length. In spite that it is very simple formulation in very simple words, it is example of unsolvable, untreatable, and very hard problem from scheduling theory and from computer science. It is a classical example NP-hard problem. And next slide, please. What is important for our survey? Many years ago, it was 1976, 1977, 1978, 60 years ago, about independently, Nikos Christofidas in the United States and Anatoly Serdyukov in Novosibirsk in Russia, they discovered and constructed algorithm which is approximate and it guarantees inaccuracy 1.5. It means that solution which is provided by this algorithm, it is always, in all cases, independently on the size of the problem, size of the graph, data which can be small and large, and the mixture, in any case, inaccuracy will be, or accuracy, it can be said, it will be 1.5 times in comparison with the optimal solution. In spite that this algorithm cannot find optimal solution, even in the worst case, in practical it may be much better. In the worst case, and gives mistake 1.5. And this algorithm is based on two ideas. Constructing minimum spanning tree, which is solvable, which is treatable, which is simple problem, solved in polynomial time, and finding complete, or in other words, perfect matching. If there will be some question, I will tell later what is this means. But the main fact that we combine together arcs belonging to spanning tree and arcs belonging to matching, also Christophidis and also Serdyukov, they prove that accuracy will be good, and mistake, relative mistake, will be not worse than 50%. This is classical algorithm which is studied practically in all universities all over the world, and usually in many universities this algorithm is called Christophidis algorithm. Even in Wikipedia it was called Christophidis, and only in during the last year, maybe 1 year and a half, this mistake was corrected, and now you can find in Wikipedia description of Christophidis Serdyukov approximation algorithm with performance guarantee. Next slide, please. What is interesting, when many years ago, 6 years ago, this algorithm was discovered, all researchers, all of us who were studying combinatorial problem, and especially traveling salesmen, we thought that now some window is open. Now algorithm of Christophidis and Serdyukov gives estimation 50%, but some additional effort and we will obtain 40%, 30%, 20%, and we will obtain better and better solution. But it was illusion. It was mistake. 10 years passed, then 20 years, then 30 years, 40 years, 50 years, and no algorithm was obtained which is better than Christophidis Serdyukov algorithm. No. And this is very attractive, very intrigued, open question to find algorithm which will be better. Okay, it will be approximate, but estimation better than 50%. Now, I want to say two things, two remarks. First remark, first of all, let us look how simple and how elegant this algorithm. It is beautiful Christophidis Serdyukov algorithm. Step 1, we find minimum spanning tree. Step 2, we select only those nodes which have odd degree, for example, 3, 5, 1 degree is odd number. Then we find, we can construct subgraph of G which contain this odd nodes, nodes with odd degrees. Next step, we found perfect, or also it is called complete matching on this last subgraph. And when we unite together arcs of the tree and arcs of the matching, we obtain what is called Eulerian graph, graph of Euler, and in Euler graph, no problem to find Euler tour. It can be done in linear time by Euler algorithm or by Fleury algorithm. We know how to do this. And when we construct Euler algorithm, after this, after we construct Euler tour, it is a solvable problem. We convert Euler tour into Hamiltonian cycle because the cycle of traveling salesman, it is of course called in graph theory, it is called Hamiltonian cycle. What is difference? Only one small sentence, that Hamiltonian cycle should visit all nodes exactly once, and Eulerian cycle bother about finding similar cycle, but it visits each arc exactly once. It is solvable problem. Okay, and please next slide. Please next slide. Okay, and now my second remark. Quite recently, it was 2020, only 1 year ago, 1 year and a half ago, and Carlin and her co-authors suddenly found what is called a slightly improved approximation algorithm, slightly improved algorithm of Christophidis and Serdyukov. You will be interested. What is improvement? Maybe by 1% or several percent, or maybe many percent. No, improvement is very, very small. It is interesting only from the viewpoint of mathematics. More than that, the proof is not trivial. Proof requires stochastic trees, and also this algorithm, new algorithm, use ideas of Christophidis and Serdyukov. It is much more complicated. What is improvement? Instead of 3/2, 1.5. Now estimation, this what is called guarantee, this algorithm with performance guarantee. What is guarantee? 1.5 minus 10 in power minus 36. Of course, it is a sort of mathematical humor, because this estimation is improvement negligible from the viewpoint of practical results, from practice. But mathematically, theoretically, this is first improvement during 60 years after the development of Serdyukov and Christophidis algorithm. The open question is how improve further this estimation. This question which we want to put in big letter, and maybe it will be interested to the students, to the PhD students, to young scientists and young researchers who are interested in this area. And in the practice, Carlin and her co-authors, they noticed that when they look for practical computation, in all the computational experiments, in the middle, in the average, estimation of error was much better, 1 and 1/3. 4/3, but it was only experimental without any good proof. Even they could not prove any theoretical improvement to this result. And now, please, next slide, please. Next slide, please. Next slide, please. Okay, here we again want to say that this is a good open question. And one more remark, that in spite that travel insertion problem very well known in combinatorial optimization, in scheduling, in discrete mathematics, in fact, in recent years, it is more and more useful, more and more helpful, more and more applicable in robotics, in scheduling of robots, and in scheduling of drones. In our survey, we give reference to several papers where scheduling of traveling salesmen, when this scheduling problem is used for good tours, for drones, and for families of drones. Drone, it is unmanned aerial vehicle. Bangladesh is called UAV, unmanned aerial vehicles. Next slide, please. This is for those people who want to know what does it mean complete or perfect matching, and the reference we give reference to this paper where exact method for traveling salesmen are used for drones, for situation when we have a communication system located on a flying vehicle, a small flying airplane. Next slide, please. In our next chapter, in fact, it is the same chapter, but we called this algorithm almost optimal. Here also we have algorithm with performance guarantee, but what's interesting, it is not 3/2 or 4/3. It is arbitrarily selected small number epsilon. For example, 1/10, 1/100, and so on. And for some scheduling problem, not too many, but for some scheduling problem, there are good approximation algorithms with performance guarantee epsilon, which are called full polynomial time approximation scheme. Detailed description and mathematical introduction can be found in paper version and also on this slide. What is interesting, I do not see, but maybe you can see this slide better. You can see that the first almost optimal algorithm were discovered in United States and in Russia. It was Soviet Union. Algorithm by Babat, Jens Levner. In the United States, this was algorithm by Sachny and Ibarra and Kim and some other authors. It was 75. It was 45 years ago. Now, in the literature, in the internet, in journals, and in papers, you can find many other almost optimal algorithms which provide a very good solution for more difficult, more complicated scheduling problem. Next slide, please. And in our survey, we gave several examples. For example, we describe a paper by Liu and Wu of 2016, where this almost optimal algorithm is constructed for flexible supply chain. Kasem-Levner, this is deteriorating jobs on a single machine, deteriorating when times are dynamically changed. And please, next slide. On the next slide, you see several other examples. Next slide, please. You can read several other examples of scheduling problems with almost optimal solution. For example, you see, no, next, please. Next, please. Next slide, please. Next slide, please. Yes, for example, paper by Yin, paper by Zhao and Xu. All these details can be found in the bibliography, in references, in the paper survey, in the paper version of our survey. Next slide, please. One of the best new results, it is a paper which we cite on our next slide, which is Hallman, Klaben, Orlin, and Simchi-Levy, which constructed first almost optimal scheduling algorithm for stochastic problem, for stochastic scheduling problems, and for this aim, for this goal, they constructed almost optimal algorithm based on absolutely different ideas. This is also very interesting direction for future research. Please slide, please next slide. Okay, and our last chapter, which I need to describe very shortly, but in details you can find in paper version. Scheduling are used for robots, and these robots are everywhere, in any area on Earth, on the sea, in the space. You can see robots, and these robots demand more complicated scheduling, and these scheduling algorithms is a new direction which are found in the recent year. Please, next slide. We give reference to recent papers. On this picture, you can see, as example, robot which is on a ski in mountains, robot which in drone which provide pizza, robot which is dancing, robot which is giving medicine, robot which collect a car, and so on. Next slide, please. And my last minute and my final seconds, which are given to me till 2 o'clock, and of course I will finish at 2 o'clock. Next slide, please. I want to tell you that one of the bright and absolutely new application of scheduling and robots, it is what is called flying unmanned station in airborne communication networks. You can read about this in papers by co-author, one of the co-author of the survey, in papers on Vladimir Mironovich Vishnevsky, several papers. Next slide, please. And several scheduling and optimization problem related to this airborne communication networks is optimization of this network, optimization of the number of these drones, how many drones, optimization of types, which types of these drones, what are their characteristics, so that aims which are existing for these groups, for these big families, usually these drones are working in big swarms, but it means in big crowds of drones. And what is scheduling without collision, scheduling with cooperation? It is one of the most interesting open question, which is topic of current modern research. Next slide, please. Yes, I told her already, number of flying stations, number of flying drones in order to provide the aim, for example, the better collection of data, the better saving of people who should be saved by these drones, and so on. Next slide, please. This is here you can find description of some of scheduling problem related to drones and mathematical results which we obtained recently, that one of this problem of minimizing the number of drones can be reduced to very well known assignment problem, and it can be solved in polynomial time. If assignment problem is m times m on matrix m times m, polynomial algorithm which we constructed is cubic, or capital of M cube. Next slide, please. Next slide, please. Next slide, please. We mentioned several attractive directions for future research, including real-time scheduling, scheduling in clouds, scheduling with communication delays, scheduling of groups and families of these drones, thousands of drones. It is an interesting direction for future research. Next slide, please. Bibliography for interesting people. Next slide, please. Thank you for your attention. Of course, I use my time. Maybe all possible questions I can answer by using internet and personal contacts.
Thank you very much, Professor Levner. Question, please. No question.
I believe now it is time for dinner, for lunch.
Yes.
but maybe after lunch there will be some strong question, and I will be happy to answer by using email and the internet.
I have one question at the very end, sir.
Professor Krieger, please.
Yes. With the examples that you have shown, energy is a very important side constraint, a part of performance. So has this two-dimensional space with the delay times, deadline-oriented scheduling, plus energy optimization been considered?
I am familiar with many scheduling problems in which energy saving is used either as criteria, minimum, for example, of some objective function, or like constraints in problems which are like mathematical programming constraint, or mathematical programming with integer variables. So I'm familiar with these papers. They appear exactly in recent years. And if you're interested, I can send you the list of these papers known to me.
Thank you very much.
Thank you. Another question? No question. Now we have 30 minutes coffee break. Thank you.
30 minutes, Vladimir.
Да, 30 минут.
You, Professor Levner.
Vladimir, thank you for your support, for your patience, because I was exactly down. I was in shock that my computer was not so good, not so well.
No problem, Kenny.
No, it's well known when we are speakers.
I try to be in time. Nevertheless,
Okay.
I try to describe our results and our ideas just in time.
Yes, we are following the schedule. Thank you very much. Okay. So turn off microphone.
Dima Kozirev, are you here? Dima?
Hello, can you hear me?
Dima Kozirev.
Okay. Camera. Hello, Luis.
Hello, Konstantin. Can you hear me?
Yes, I hear. Moreover,
What a pleasure to see you and hear you.
Thank you very much. Thank you very much. Yes, I'm dreaming about of cup of coffee with you physically.
Yes, yes, yes. Well,
I do hope the time will come. I do hope.
Yes, we are. I think you already got the email that the new cost action will start, right?
Yes, yes, we are ready with Yulia Gaidamaka. We are ready.
Yes. So, hi, Julia. Hello.
Hi, Lewis. Nice to see you. How are you?
Julia, don't forget, you are at international conference.
Yes. Lewis, you are looking very fine. I think it's plus 20 in Lisbon. Yes, am I right?
Yes, it is. Yes, yes, yes.
Yes, we have plus 2 and raining.
Really?
Yes, this is September in Moscow. It's normal. It's okay for us. Yes. So please enjoy. You are living in heaven.
Yes. Thank you. Thank you.
You will make presentation yourself, or we can play your presentation from our side?
I propose that I can just give a 1 minute introduction, but then I've sent the file this morning. I think it's better that you play the presentation because there can be connection problems. And then in the end, once the presentation is finished, I can come back live and answer questions and discussion.
It's okay. We are ready. We are ready.
Yes.
Let's wait for a couple of minutes, and then we will continue.
Yes.
Yes. Okay, and just yes, after break we are continuing our plenary session. The next speaker is Professor Luis Correa from University of Lisbon. I can say a few words about Professor Correa. You can find also his CV on the site of the conference. I know him personally, yes, and I'm looking through his CV and I'm pointing out a number of very outstanding things. For instance, he has participated in 32 projects within European frameworks. Yes, having coordinated 6 and taking leadership responsibilities at various levels in many others, besides national ones. He has supervised over 220 MSc and PhD students, having edited 6 books, authored over 500 papers, and so on. And internationally, it's more important for us, he was part of 37 PhD juries and 71 research projects. Lewis, Professor Correa, he is at the board of the European Commission at COST projects. Before it was IRACON mission, and just now Interact mission, which is devoted to the radio access networks of 5G and now of 6G networks. That's why Professor Correa can make concrete presentation regarding 5G and 6G networks, problems and challenges. And so, Lewis, you have time to say a couple introducing works, and then we will play your presentation. Thank you. The floor is yours.
Thank you, Konstantin. It's a pleasure to be here today. Unfortunately, the pandemic does not allow us to meet our friends physically, at least not yet. We all hope that in the very near future, we'll be allowed to get together again. So thank you very much for the invitation to give a talk at this conference. It's a pleasure. And again, as I said a few minutes ago, and probably some of the colleagues have heard it, I've prepared a recorded presentation just in case we have connection problems. And then my proposal is that after this recorded presentation, I'll be back live, and I can answer all the questions and all the comments that they may come from the presentation. So I propose then that you start with showing the presentation, please. Thank you.
Okay, thank you very much, Lewis. Everybody understand that after the presentation you can put your question, and Professor Correa will answer you in live. Please start.
So
A few minutes, some technical problems on our computer. Let's wait a little. As usual, dual trying, everything is okay.
I can give the talk live if there are any technical problems with the presentation, of course.
Yes. Wait a little, Lewis. No
okay.
problem.
It's okay. Thank you.
I will ask you if we can scope.
addressing the of title 5G and 6G networks and trying to bridge a little bit. Thank you, dear colleagues, for the invitation to share with you some of my ideas and concepts about the future of networks in mobile and wireless communications. I'm Luís Correa. I'm with IST in ESCID, which are part of the University of Lisbon in Portugal. So basically, I'll be addressing, as you saw from the title, 5G and 6G networks and trying to bridge a little bit, not only between these networks, but also towards the future, of course. I'll start by looking at the history of other technologies, so that by using this knowledge, we can try to understand a little better how we can imagine the future and the evolution of mobile and wireless communications. Then I'll address terminals and services as key aspects of the needs and the requirements for the systems and the networks of the future. And then, of course, I will dig into the networks, more the networks aspects rather than the system ones. And then I'll end with the conclusions of this talk. So let's start with computers. Computers started many years ago, of course, but some of you do remember the old times, let's put it this way, in which you had the mainframes occupying a vast room, vast areas in a room. And then, of course, everything evolved to the personal computers, and you know the rest of the story. Also, in parallel to these, it was really crucial that instead of having commands to move information and to process information, we start having windows, of course, with everything that we do with the mouth these days. So the key concept here is that easiness of use is essential for the mass market, and it has been, of course, in the case of computers like this. Also, in the case of computers, also some of you, the old guys again, may remember many years ago, roughly 40 years ago, when we had the appearance of the ZX Spectrum, which was a very personal, preliminary personal computer. You can see here the characteristics. So the clock was 3.5 megahertz. The RAM was 16 kilobyte. It had no hard drive. Of course, the evolution since then up to these days is well known again. The key message here is that as we have a progress in the electronics and the hardware capabilities, of course, software is going to eat, if I may allow this term, is going to eat all these, and then somehow there has been a race since then between the software and the hardware, meaning and the capabilities that we can have from the hardware that is made available to us. This is a little bit what has been happening in mobile and wireless communications as well, not only with the networks, but only with the computers, of course. Now let's look at a completely different area, which is cars. Cars started again roughly a century ago. John Ford in the United States, he said that basically he could sell cars as long as people choose the model he wanted to sell, more or less. Not exactly like this, but this was the idea. You can sell whatever color as long as it's black. But the idea here is, okay, this was the beginning. And the beginning of selling cars was really to have faster cars. I mean, cars needed to be faster than horses, basically. That would be the motto for selling cars. Then, of course, there was the technological evolution of cars, and speed wasn't that important anymore, basically because we cannot drive a car at 500 kilometers per hour. We don't have roads to do that, apart from many other aspects of security and so on, and safety. So basically, cars evolved towards the comfort of users, the safety of passengers, and these days, even all the things are done, and cars are being sold for energy efficiency. Energy being electric cars or even diesel or whatever, it's really the key issue for selling a car. So speed is no longer important in cars, and this makes a difference how well we face a car these days. Another area is clocks. I mean, by this time you think, why is this guy talking about these things? Well, wait a few minutes, please. So let's look about time. So in the beginning, time was about having a single clock in a village, right? You have a top of a tower, and you would have on the top of a tower, you would have a clock with some bells, and every hour you could hear the sound of the hours. Then, of course, with the evolution of technologies, we start having a clock at home. I know this is a grandfather clock, like the ones I'm showing here. Then again, it's making some noise. And then every hour or every half an hour, we could hear the hours, the right hours, right? Then, of course, again, we all know how this evolved. It started with the pocket watches, then the wrist watches, and every day. The bottom line here is that nowadays we live surrounded by clocks. The question for you all is, in this point in time, is does anyone know exactly how many clocks you have at home? Because if you ask me this question, I'm not sure. I mean, I need to take a few minutes to count how many clocks I have, from the computer to the microwave oven to whatever it is that we have clocks. So the spreading of digital technologies, as you see, has led to the commoditization of time devices and to the generalization of time devices for having. This is a little bit what is going to happen, started happening, will happen in mobile and wireless communications. Now, finally, the last technology I want to talk to you about is pens, writing, right? Then, of course, people start writing with feathers and sticks. Then, of course, even before that, you can consider that people would carve on stones, these kind of things. Then, in the 19th century, there was the metal point pens, and these really revolutionized, became the way that industrialized more even the way that we write. Then, of course, we have this company with big, that had these very easy to use, let's put it this way, but also very cheap pens. And then, of course, this completely made the writing a very affordable to everyone, whatever device we could use. These days, as you know, we have luxury pens. They are often offered to people in some conditions, and they cost a lot. And this means that we can transform luxury into luxury devices, products that are commoditized and they are very cheap. And of course, I'm not even talking about the stylus that we used to write on iPads and tablets and computers these days, which are some kind of electronic pens. So why all of these? Well, because we need to start thinking about terminals in mobile and wireless communications in a completely different way. And looking at the differences that we have from the past and looking at these other technologies' evolution, and try to see how these will be important for the evolution of mobile and wireless communications. You can see here on the top the evolution of phones. With these very first on the left is the analog 1G phones. And of course, it evolved, as you know, to what we have today known as the smartphones. But we also have terminals which are watches. And there are several manufacturers doing smart watches these days with which you can talk also. Of course, Google some years ago made a product of spectacles that at the time it was communicating via Wi-Fi. This was in almost 10 years ago. Time flies, really. They withdrew it from the market, but I'll come back to this in a minute. And of course, these days, many people, and then I say many people, I say mostly, of course, let's say in advanced economic countries, whatever you may call it, many people have three terminals these days. We have a mobile phone, we have a tablet, and we have a personal computer. And if you really look into these, you will see that there's pretty much no difference between these terminals from the viewpoint of what we can do with them. I mean, we can make a call, we can access the internet, you can browse information, you can write a document in any of these three terminals. We use one or the other more because of the comfort of exactly having the size of the information or the easiness of use or whatever it's in. So this terminal thing will evolve definitely. And we see, for example, already an evolution that is started to happen already in what I would call in the area of body area networks. And this has to do with certain areas of professional areas or even beyond that. But I've put here military, police, firefighters, civil protection, sports, and others, medical professions as well, and so on, in which you have uniforms, in which you have embedded communication devices. These days, it's very common that you have in a police uniform, you may have a camera and a communications device. In military, you can even have other things. In other kind of wearables, like what it's called smart textiles with sensors that sense the excuse me, that sense the heartbeat and all these things. So we can think that in the future, in the very near future, we have a lot of terminals, and in fact 5G is already pointing in that direction, terminals which are non-direct personal and industrial usages for IoT and all the kind of things that you can see here in these pictures, and I will come back to this in a minute. But let me call attention to something that is already for sale for some years now. So this jacket, starting being on sale in 2006 from Burton Motorola, and this is an embedded FM radio in a winter jacket. And you see here that you can hear the sound in here. So this is a product. I mean, you can buy it these days. Then you have the sneakers that were introduced by Nike in 2006 as well, together with Apple's iPod. So this would count, was the beginning of, let's say, the personal sensors, counting the steps and all the things that we can do. Then if you are concerned that you go to the middle of the wilderness, a forest, and you have energy, you have this backpack with solar panels, so you can feed your devices, your personal devices, from these solar panels in the backpack. This again was on sale since 2006. And even more, in 2009, you have this jacket from Hermenegildo Zenya, in which you have solar panels in here. So you see that putting stuff, and when I mean stuff, I mean electronic devices, in clothes, for example, has been around for a number of years. So it's just allowing for the technology to evolve and to let us take advantage of all these things. More recently, in 2019, I had the privilege of being in a conference in Valencia, in which it was the first demonstration of full-size holographic conversation. So you had someone on stage, and you had an holographic image of a person doing a 5G call in real time. So this means that having holography in terminals is just a matter of waiting a few years, and the technology will evolve so that we can have it in our phones. I don't know if you noticed, but this is being recorded in September 2021, and a couple of weeks ago, I saw on the news that Ray-Ban, which is a United States spectacles manufacturer, made a partnership with Facebook, and they start selling these spectacles in which you have the cameras here, one in here and one in here, and these spectacles allow you to film and to see things, and this has a Bluetooth connection with your smartphone. So see, having other kinds of terminals, so this is, let's say, an evolution, if you can call it this way, of this Google glasses or the Google spectacles that were launched some years ago. So you see, terminals are evolving, and we do have a lot of other terminals being accounted for. So this means that services are going to evolve as well. And services, definitely with 5G, will not be only for humans, for people directly, but also for machines, which means humans indirectly, right? So I'm sure you know this triangle. It has been circulated it has been proposed by ITU, the International Telecommunications Union, in 2015, and basically has the three pillars of 5G. So one is data rates, enhanced mobile broadband. The second one is massive machine time communications. And the third one is ultra reliable and low latency communications. And you see in here some examples of services that use this. So what does this mean? This means that we need a high data rate that we can have up to now, a higher capacity from the one that we can have up to now, and a lower latency, again, compared what we have up to now. But why do we need these? Why do we need to keep evolving in these three axes? Well, let me show you why. So why do we need high data rates? Okay. I'm not going through the whole table in here, but this is just the data rates we had since GSM in the very beginning up to 5G now. And you see that, of course, depending on the size of the files, you see here the times it takes to download a file. So, of course, if you just want to send an email with 10 kilobytes, then even the very old GSM does it in 8 seconds, which is affordable for most of us. But if you go down to the table to a film in 8K, which is the highest resolution you can have these days, and this means that the size of the file is around 800 gigabyte, then even with 5G, it takes almost 2 hours to download the file. So we still need for some applications, and I could mention here also augmented and virtual reality. I'll come back to this in a minute. There are still some applications that are really requiring high data rates. That's the race I told you about in computers. When the hardware, when the networks, when the system gets better in technology, then of course you always get applications that take advantage of it. That's what's happening here. The need for low latencies is another one. In here, I would like to split this into different areas. Let's say one is people, humans, the other is machines. So in humans, if you want to catch a fly, let's put it this way, you need reactions of the order of 1 second, which is, okay, you understand. Then, in sound, we tend to a human being tends to be sensitive to delays lower than 100 milliseconds. That's how we can notice that there is, let's say, a problem in communications. And for those of you that know the old telecommunication networks, you may remember that 100 milliseconds was really the maximum delay imposed in the network for a conversation to be accepted as of good quality. Then we go to the synchronization of sight and audio, and this goes down now to 10 milliseconds. So this means that we are seeing TV, for example, the news, and we start seeing a reporter that is talking from somewhere in the world, and sometimes there is no synchronous behavior of the reporter's sound and video, meaning the reporter is talking, but the lips, we don't hear the lips synchronized, right? So that means that this lack of synchronization that has to do with the processing of information, of course, from a long distance, but doesn't matter now. So this means that this is in the order of 10 milliseconds. So we are sensitive to 10 milliseconds when it comes down to synchronizing sight and hearing. And then if we put everything together, sight, hearing, and trying to get something, so our reaction time, we have it down to 1 millisecond. So this means that things that put together the three senses, and this has to do, it comes again to virtual reality and very new applications that come with 5G. 1 millisecond is really the time scale that we need to take care of. And here we go, like some of the new applications that have been foreseen for 5G, as, for example, remote surgery. In the area of machines, robots, of course, robots can communicate and react at much lower time than users, human people, I mean. And here, again, we do need reaction times and communication times in the order of 1 millisecond. Finally, the high capacity. Why the high capacity? Well, because we want to connect everything. We want to connect just not phones, as it has been up to now, but we want to connect cars. We want to connect our electrical appliances. We want to connect transportation. We want to connect whatever is connectable. So, of course, this means that a huge connectivity needs to be available to put all things available to everyone. So this means that we are definitely changing the way that we deal with a lot of things. One is information. We are in what we may call a paperless society. Most of the information we process these days is no longer printed on paper, is of course sent to us electronically via email, or we have it access to it via the internet. So this means that networks need to be prepared for these. The other aspect, of course, has to be dealt with location. We can consider already a very old thing that we know where we are. Our phones these days, of course, have GPS and other location processes via the cellular networks and Wi-Fi that enable us to know where we are. But networks start evolving in another area, which is networks knowing where we are. And when I mean knowing where we are, is not knowing where specifically each one of us is much more in the sense that using our phones as sensors of the channel, as the network, as the quality that is provided. And anonymized, of course, we are not discussing here privacy issues. We are discussing terminals that can be used as sensors to the network and to provide a better service to every one of us. We have, of course, Internet of Things, but mobile Internet of Things, again, we are putting sensors everywhere, and 5G is definitely providing the means to have machines communicating to machines, as we have already these days many examples, as you know. And this also means that putting sensors in clothes and a lot of objects that surround us on a daily basis will be, of course, let's say, very common. And this means also that we need to start differentiating, as I think you already got the idea, between human and machine traffic. It's really very different. We need to do this. So service differentiation, traffic differentiation is of essence, is essential that we provide good communications for everyone. Then we have all smart cities. I mean, smart cities these days became a very well-known topic. I will not go into the detail, but smart cities means that basically we are going to put everything into the same bucket. So you have all these areas. I've put here a few of them, which has to do, of course, with transportation, with health, with public information, with energy efficiency, environment, smart grids. Again, the list is endless, and everything will be ready to be put into the same network to communicate and to integrate into several layers, of course, of networking. Then we come to the multiple realities. So these days we are prosumers. Prosumers is when you concatenate producers with consumers. This is what we are these days. This means that we upload and download information in the network almost not exactly one-to-one, but probably two-to-one. So meaning we are uploading a lot of information, photos in social media, videos, of course, besides all the files that we do. And this means that networks need to be prepared for that. And also, of course, augmented and virtual reality. They are already available these days. You can buy glasses on these things, but they are not connected yet to the network. But 5G will enable these, and I think that this will be really the 5G differentiator for, let's say, consumers out on the street, for us as consumers. Is products based on augmented and virtual reality. This is what 5G will make the difference compared to 4G. Then we go back to, let's say, the roots of some things, and this means body area networks. Body area networks are networks that are established around our body with sensors that are put in several ways. They can be on the clothes, as I mentioned, but we can have sensors that can put on the skin, for example, or we can have sensors that can be put inside our body. We can, for example, swallow a pill, which is not a chemical pill, but is a mechanical pill, for example, for do some diagnostics in our digestive system, right? These kind of things. So, of course, this means that we can consider that we are starting the era of truly personal communications with many applications. You see here, medical, assisted living for the elderly, but then we go to other things like entertainment, sports, law enforcement, the military. there are many applications that can be envisaged for all these area of the body area networks. Again, a lot of sensors and communication devices and wearables that are somehow connected to our body, to our clothes, and that all communicate, sensors and actuators, by the way, not just only sensors. Vehicle communications, it's another area that is developing a lot with 5G. We start seeing autonomous cars around the world. It's definitely a technology that is picking up. Still very much in its infancy, but we need networks to provide a lot of information and for this kind of communications, transportation better than communications. As you probably know, when fast trains started or high-speed trains started, communications was essential. And GSM-R, in fact, was the train communication system that was established to provide a background, a communications background for high-speed trains. So now that we are start to having vehicular communications and autonomous vehicles, we need again communications network to make this happen. And 5G, when what it comes after that, will definitely be the communication system to be used. What about any future services we may consider? Well, again, holographic images, mobile through the internet. As I said, I think it's a matter of time to have these. I told you about this very first 2 years ago, very first trial of holographic phone call in 5G. Of course, you can have other, which seem futuristic by these days, context-aware mobile communications, in which our phones are aware of our physical and social moods. This can be done easily with sensors and, of course, artificial intelligence on data processing. We can have, again, interactive context games in which you can be in a building and you can start killing aliens inside the building, meaning as a game, of course, meaning that you have 3D images of the buildings, which is, of course, this is already happening. Most of you know that Google already provides the inside views of many public buildings in many countries. So the technology is there. It's just a matter, again, of having it common to everyone. And finally, still dealing with these applications, I would like just to mention a few of them that start being already foreseen as the key ones for 5G. Virtual reality, so the use again of virtual reality in industrial applications is definitely one of them. Remote control, in which you can control machines from, let's call it a control center somewhere in an industry. You don't need people to be there, and this can be, and this is essential to be used, for example, in case of an earthquake, you can send machines or, let's say, very hostile environments for humans, and you can put machines there and you can control remote them. Robotic automation, again, here we come again with robots. These lines, production lines that you have in, this one is for cars, but of course you can see it for many other processes and industries. These days, this is a must. And of course, you need reliable communication systems, and 5G and wireless and mobile communications can provide a huge cost decrease, and besides decreasing the cost, you have the increase of inefficiencies. You put the two together, and it's, of course, very good for industry. And also automated guide vehicles inside logistic factories and hardware warehouses and all these kind of things. You don't need people, humans, you don't need people to go there and pick something. So these are really what is foreseen to be some of the key industrial applications for 5G. So just to close these aspects of services and applications, as you see, we have the old stuff, which is voice and video conference, geolocation, file transfer. We have now new ones that are becoming available with 5G. Again, augmented virtual reality, robotic automation, biometering, all the stuff with the sensors and actuators and mobile IoT and many things else. And the key message here is that service differentiation is paramount. It is essential that we differentiate services, because if we don't, then networks cannot provide the requirements, the services according to the requirements that they have. I've put together here a graph that enables to see how service differentiation is essential. On the one hand, you see on the left, you see latency. These are log scales because the differences are so high that we really need to use a log scale. So this is latency in milliseconds, and the bars are red on the left. And then on the right, you have data rates in gigabits per second, and the lines are red on the right. And this is, again, is also in a log scale. So for example, you see here very distinguished needs, and that's the basic idea of this graph, is that very different needs for several applications that I put in here in terms of latency and data rate. You see here, for example, that for industrial safety control, you need something in the order of a very low data rate. I've put here in the order of a megabit per second. Indeed, you just need to send commands. So there's not much need of a high data rate, but the latency needs to be lower than 10 milliseconds. On the other hand, you see it is, for example, again, industrial motion control, in which the latency needs to be in the order of 1 millisecond, and data rates are relatively low. Again, let's put it this way. But you have others like virtual reality that can be, and you see the colors here, so red is for consumers, green is for business or industrial, and blue is mixed. So virtual reality, which of course can have both a consumer and an industrial application. And you see here that the latency is relatively low, 10 milliseconds for the latency for virtual reality, because of the things I told you about how humans react to stuff. And then you see that the data rate also needs to be very high, definitely higher than 10 gigabits per second when you have a number of people. This is not just for a user, but when you have a number of people using it. So these are the needs that 5G need to respond. And now you see the needs for service differentiation then. The networks need, again, to take these services and applications differently and react to them and process them in a different way. This other graph here, I'm showing here the evolution. And of course, we see that, again, latency on the left, latency with the different generations has been decreasing. The goal for 5G in the version of ultra-reliable, low-latency communications is 1 millisecond for the reasons we have seen. And you see that the data rates have been increasing. So there is this trend that with the generations, data rate is going to increase. Here on the right in red, my apologies. And then the latency on the left in blue has been decreasing. And this is really what we can expect in the near future as well. So this means that we need to start having different categories of services. I've shown here just three. Best effort, everyone knows what it is, of course, but we need to start having other types of categories of services, of service level agreements. For example, can have something that has a maximum bit rate, which can seem to be strange. I mean, why am I imposing a maximum bit rate? Well, because there are services that don't need more than that. Voice is definitely one of them. I can have an excellent voice quality with something like in the order of, let's put it this way, a few kilobits per second. I don't need 1 megabit per second to have a voice communication, and definitely not 1 gigabit per second. So there are services that can have, let's say, a maximum of data rate, and we can perfectly live with that because they even have a huge quality, if I can put it this way. So now let's change a little bit now into the network aspects. The problem that operators have these days, and we cannot forget that operators are the guys that provide the services, they have, of course, an increasing traffic volume because of data, but revenues is not increasing in the same way because in many countries you have these flat fees and everything else. So there is a huge difference that is increasing more and more also between what they get as a revenue from us as customers on the one hand, and the needs for traffic and for capacity, and of course the investments that go along with it. So this means two things. means that on one hand, the operators need cheap technologies or cheaper technologies to be implemented. On the other hand, they need to increase the size of the market. And 5G is a good answer for that. 5G is a good answer because on the one hand, the market is going to be augmented, to be increased, to be reaching industrial applications. So the market is definitely, with mobile IoT, is definitely going to increase. On the other hand, of course, with the network aspects of 5G that I'll be addressing in a minute, then technology becomes much cheaper with Open RAN and a lot of technologies, and these somehow, let's say, makes it favorable for a good evolution of the technology for us, for operators providing the service, and for us as consumers. Of course, again, we need to leave definitely this one-size-fits-all that we have up to now, having the same network, doing all the same things for the different services. And again, service differentiation, now that we are entering into the era, or we have already entered into the era of data and voice, we need to do differentiation in between the services. So this means that what we have had up to now, which was somehow the motto of the Olympic Games, which, as you may know, is Citius, Altius, Fortius, which means faster, high, and stronger. And even this year, we had another edition of the Olympic Games. Basically, it means more of the same, but just better. We need to get rid of these. We need to have disruptive views on just to change things. And again, in the network area and also in other areas, we are definitely going in this way compared to mobile communications. But let me even tell you another perspective. And I'm bringing here a speech that John F. Kennedy, the President of the United States of America, did many years ago, so the May 25th in 1961, in which he said, and I quote, "I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the earth." What I mean with this is the following. Say, this guy was not saying you need to develop rockets, you need to develop Velcro, you need to develop seat belts, you need to develop faster communication. Is what I mean. These all the things I just mentioned were consequences of this general goal of a huge challenge of putting someone on walking on the moon. So what I'm not saying that we need to put someone back walking on the moon. What I'm saying is that probably we need, for the evolution of mobile and wireless communications, to set up a goal that is not based on the evolution of current technologies, but what we want to achieve. And saying, for example, that we want in 10 or 20 years from now, someone that can be capable of transmitting any information that he or she wants with any device that is available to he or she in the area of a personal area network or the body area network, blah, blah, blah. So a more general goal, and then we start seeing how we can implement this general goal and what kind of technologies we need to implement to achieve this goal. So what will be the goal of 6G? I don't know. No one knows. If you look, I tried here to put the goals and the problems that the several generations up to now have solved somehow. So the first generation presented voice. It was only voice. Second generation 2G had already solved the problem of voice, is good quality with GSM, and starts introducing data. It's still at very low indeed data rates. 3G kind of solved the data rate problem. But I mean, with 3G, we can have data rates up to 10, 20, 30 megabits per second, which is already very good for most of the things we can do these days. But then there was the problem of capacity. And then 4G somehow solved the problem of capacity and enabling a lot of terminals to be connected and with a decent data rate. Now 5G is coming, and 5G has solved the problem of latency that we had up to now, enabling again to connect many other terminals, namely industrial, as you see, and services like, again, virtual reality. What is 6G going to solve? I don't know. I put here 3 things. One is availability. Everyone talks about the many nines, 99, 9999, whatever. And availability means that putting together Wi-Fi with cellular and many other things into the ubiquitous networking aspect. Another one is intelligence, bringing more intelligence or bringing intelligence to the network with all the tools that we know these days of artificial intelligence, machine learning, and all the stuff that we know. Another problem to be solved may be terminal sharing. As I was saying, I can use any terminal. I can go to the hotel room and start using the TV set as a personal terminal, for example. And many other things, having the car, when I enter the car, automatically the car senses there and all the devices in the car connect with my personal profile and so on and so forth. So again, these are all things that probably can be achieved with 6G. We need to wait probably 7, 8 years to know what the answer is to this question. Let me briefly address the matter of radio. I'm not going much into radio aspects, but just for you to understand what's happening these days. Radio used to be, and I'm saying used in the past indeed, used to be the differentiation generations. 1G was FDMA, 2G TDMA, 3G CDMA, 4G OFDMA, and then 5G has basically the same radio interface. So the big difference between 4G and 5G relies, in fact, not on the radio interface, but relies on the networking aspects of the network. This is the first thing. The second one is, see, this is empty in here. So we have explored the time dimension, we have explored the frequency dimension, we have explored the code dimension. The spatial dimension starts being explored in 5G with the active antennas, beam steering, beam forming, but not as part of the radio interface. So probably 6G will occupy this empty space of having antennas, active antennas, as being part of the radio interface. Let's see how technology evolves. So now we enter in the networks. And as you know, there are 2 major differences that 5G bring, again, compared to 4G and previous networks. One is network virtualization, meaning networks can be virtualized and sliced at both the radio and the fixed components. So this means that before, and just as a reminder for those of you that are not familiar with the concept, in the traditional architecture, services share the network in a competing way. So there is no service differentiation and all these things that I mentioned. And I mean, everyone is fighting for a few bits per second. In network slicing, you have slices of a network. Means that parts of the network are isolated from each other. So I can, for example, put in the same physical infrastructure, I can put these transportation, mobile IoT, and say, okay, all guys in here will have 10 gigabit per second, whatever, doesn't matter now, right? And all the others, maybe there is not even capacity for people to make the phone calls with the mobile broadband, but everyone in the cars continue to use the network as it is. So this is the concept of network slicing and isolation. And in fact, this is one of the secrets in commons, of course, that everyone expects for the huge success of 5G is network slicing, because this enables private networks. Private networks means that we will have networks coming from many, 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 many industrial applications that can share the network with isolation. And we can have groups of people communicating and all this kind of thing. So we can have, again, plants communicating and dedicated usage of slices of the network to industries, different industries with different qualities of service, different qualities of experience for the users, different requirements, different needs. Everything can be put into the same physical infrastructure. The other aspect is cloud networking. Cloud networking cloud computing is very familiar to everyone. That's what we do these days when we put files in some provider of cloud, Dropbox, Amazon, whatever, OneDrive, Google Drive, whatever, doesn't matter. You know all of these things most probably. Now, how does it mean cloud networking? Okay, cloud networking basically means the following. Up to now, every base station has its antennas, its processor, everything, and then each base station, not only the radio part, but also the processing is in the base station. And then this information is sent to some common central node. What we are going to do, or what is going to be done in 5G, is that we are going to split the radio part, which we call remote radio head, from the baseband processing stuff and everything that has to do with bits processing, the baseband processing unit and everything else, and we are going to co-locate them in a single place. So we still leave the antennas and the radio in the locations that we need to provide coverage by propagation of waves, but we will have central nodes that are processing everything. That's exactly what enables networks to become much cheaper, much more efficient than everything else. So cloud run or open run, cloud radio access network, or technology these days is even called open radio access network, means that it's the softwareization of networks, right? This is about software stuff. You leave the physical aspects of antennas and amplifiers in here in the radio, then you just transmit everything via an optical fiber to computers, and then computers deal with it. So this, of course, has problems. I say, of course, because there's no such thing as a universal panacea. So, of course, this means that we have a problem here, which is we have maximum distances. We have the delay of propagation between nodes. These delays impose maximum distances. And for some services, these maximum distances will be tough. Tough meaning we cannot have large distances between some nodes if we want to implement the services that I mentioned with 1 or 10 milliseconds, this kind of thing. So this means that we are evolving already from the cloud networking perspective, which is having central service for everything, to the edge networking. And edge means that we have intermediate nodes, the MEC nodes, the MEC servers, so they are located closer to the users so that the propagation times between these guys, users being machines or humans, and these MEC nodes, these servers, are smaller so that we can indeed implement these services with 1 millisecond of delay, latency, or whatever it is. Now, let me finish with two perspectives of the future. One is global body air networks. This means that let's go inside the body. Let's put networks inside the body. Nano nodes, really very small nodes that you can put inside the blood circulatory system to detect diseases, heart diseases, for example. And these nodes can communicate to some sensor that is on the skin, and then it connects to the wearable. So you see, this is a completely new perspective for body air networks and for solving a lot of many medical applications. So global body networks do have a lot of problems. We need to characterize the communication among nodes and the gateways of the different type of sub-networks, meaning the nodes flowing in the digestive circular system or in the blood circulatory system, and how they communicate in very high frequencies, so very short distances to some gateway that is on the skin, and then from the skin, yes, you can communicate to a wearable, a bracelet, or a phone, and then to the outside world. Of course, here we have the influence of human mobility that will impose a lot of problems in these networks. We have the interconnection between the various sub-networks, and finally, the characterization of communication between the body air networks and external networks. So for those of you working in networks, there are many open problems here that need to be addressed for the near future and for 5G in general terms. The other area, which I think is full of open problems as well, is private networks. Again, it's this extension of networks of communication to a lot of industries, to a lot of usages that are not in these days. I've just put here a number of features that usually are not available in commercial networks. Some of these are available in the old because they are 2G enabled emergency and public safety networks, like one-to-many calls or emergency calls, fast call setup, reliable connections, all these kind of things. And the list is endless here when you start talking about all the needs coming from many industries in this area. So private networks indeed are a new, completely new way, I would put it, from the network viewpoint, that has to be researched a lot, because there's not much to be, or that has been done in this area, looking at the specific applications that these private networks have. We cannot have a factory with robots being treated the same way as we have been treating phone calls or people downloading files in the network. It's a completely different thing. And we need good models for these. We need good ways of looking at these different problems. So I've listed here a number of open problems in private networks. Again, the characterization of the variety of services. So service differentiation here needs to be accounted for. I told you this a number of times today. The modeling of the different types of networks and the optimizing performance and reducing costs. We need industrial applications. This is a must, I would put it this way. We need to account for the specific requirements in the management of the networks. So how to manage the slices. So we need protocols and we need algorithms, we need processes, we need to put together a lot of things. And of course, optimization, also taking the supported service and geography into account. Because of course, it's the coverage and the capacity aspects do depend on geography and where users are located. So just as a final ideas, data, of course, is a must these days that you need to take into account. And all the huge amount of data that is being available to have to us and to, of course, users, industrial users, and to network operators, enable all the marvelous tools that we have of data analytics, artificial intelligence, machine learning, and this will be brought also into the networks. And remember, I told you of having terminals as sensors to the network will play here a key role for having these usage of data for increasing performance. And finally, security. Of course, security, for those of you that work in security, we have security of networks and security of information, meaning preventing people that are not allowed to enter the networks or to have access to the information, or then to mimic the nodes or to change information. And the increasing softwareization of the networks creates many problems in these areas, you may know. And this means also that in telecommunications, we do need to take these into account. So security aspects need somehow to be embedded into the design of the networks, together, of course, with the other features that we are very familiar with today for personal use, which means privacy and trust, and all these aspects that we also need for everyone using whatever technology is. So in conclusion, I would say that, remember, I start talking about clocks and pens, which may look very strange, but now I think you understand why. Because if we look at the evolution of mobile and wireless communications, we can see somehow that we are following also what other technologies have done. And this means from that we can have some better ideas on what to do with mobile and wireless communications. Of course, we can see that the evolution of terminals and services impose major changes, and we need to take these into account when we develop new systems and new networks. Of course, 5G and afterwards 6G will be, it seems, distinguished by network aspects. 5G definitely is the case. Let's hope for 6G to see what happens, meaning the differences are not that much on the radio interface and the radio aspects. And finally, I've offered you two areas which I think need to be explored from the research viewpoint, the networks research viewpoint, course, there's a lot to be done in this area, and they will play expectedly a major role in 6G or even already in 5G. And these are both the area networks and private networks. Let me finish with two quotes that came from guys that had very important positions in two companies. One was Thomas Watson from IBM in almost 100 years ago. And he said, I think there is a world market for maybe 5 computers. Of course, this is a laughable one. And of course, IBM is no longer manufacturing computers. This guy was very much wrong. But IBM was capable of changing. And IBM is a very successful company these days. Not manufacturing computers because they had the capability of changing. Digital Equipment Corporation, DEC, was a huge competitor for IBM in manufacturing computers. And its CEO said in 1977, there is no reason anyone would want a computer in their home. Yeah, he thought it like this. So these guys did not personal computers coming. When they woke up, it was too late, and this company no longer exists. So if you are not capable of changing, you die from the industrial viewpoint. So from the research means that we need to be open to new ideas. And I would like to end with a colleague quote, with a quote from a colleague, Alan Kay, from University of California at Los Angeles, that he said that the best way to predict the future is to invent it. And I think that's what we are supposed to do in research. So thank you very much for inviting me again. And I think I'll start being live now and answering to questions and hearing your comments. Thank you very much.
Thank you very much, Professor Lewis. I see a couple of hands at my screen. First, Professor Evgeny Levner, please. You have a question, yes? Or no? Evgeny, what about your question? Because your hand is at the screen.
Maybe, yes. It is very interesting about, okay, first of all, I'm impressed, very, very impressive, very attractive lecture. Thank you very much for this lecture. And it gave me a lot of many ideas and a lot of possible new possibilities. There were a lot of things that I never heard about this sixth generation and these details. And of course, I'm interested, my question is of a very general nature. What can be done by modern artificial intelligence and mathematical approaches? What are the most attractive artificial intelligence and mathematical approaches for these networks of the sixth generation?
Thank you very much for your comment. Thank you very much indeed. It's good to know that I was capable of putting some new ideas forward. Thank you again, your colleague. Yes, I think the main capabilities that are brought by artificial intelligence and all the methods that come with it come from the fact that the sensors, the fact that we start having sensors and data coming from these sensors at the network level, at the user level, this is going to provide, or is already providing, a huge amounts of data on many things. When we use certain applications, how we use, where we use the location, what is the quality of the channel, how many people are asking a specific service in a specific time. All these kind of things can be brought into the networks, and the networks can process this information, and the networks can start guessing in commas, of course, meaning having a high probability of putting the conditions of the network to provide these services in a better way, with a better quality. So I think that, in fact, by putting all and correlating information, of course, correlating data. So then the huge amounts of data that are going to be made available need to be processed, and artificial intelligence is definitely the means to do it. I hope I have answered your question.
Thank you.
And I see one more hand. We still have not so much time, but please, Adu Iz, you have a question. Please, you can ask.
Yes.
You can put it to Professor Lewis.
Dear Professor Correa, I am Eve, a PhD student of the Applied Probability and Informatics Department, Ruda University. First of all, thank you for the very interesting talk on the challenges when transitioning to the sixth generation of mobile networks. We understand that one of the features of both 5G and 6G networks is network slicing. When the owner of the infrastructure, a mobile network operator, leases its resources to several tenants, virtual network operators. As I understand, the problems are primarily related to the combination of several radio access technologies. So it will be very interesting to know what challenges arise in the field of network slicing. I mean, from an engineering point of view. Thank you.
Thank you. Indeed, the slicing of the networks, the virtualization of the networks, it started more, let's say, in the core network, but is being brought to the radio components as well. And the fact that we have at the radio level at this moment 4G and 5G with the same radio interface, which is OFDMA, this enables that we can start looking at the slicing of radio, which means to allocate different channels to different services or users or whatever it is. The problems here rely that in radio, if you want, for example, to create isolation, and isolation may be seen as providing a fixed data rate, users are moving, they are not static most of the times, so radio conditions change, the channel changes, and this means that the number of resource blocks, the number of elementary radio channels that you have to allocate to the user will change as well. So there are very tough problems in radio resource management to deal with this isolation to provide good slicing of the networks at the radio level. And of course, this gets more complicated if you are going to put these with several radio interfaces, because then you are dealing with different ways of managing the spectrum. Then it gets even tougher.
Thank you. Thank you, Professor Correa. I can't see other hands in the auditorium. So, please accept our compliments for your brilliant talk as usual, dear Lewis, and we are waiting for you for Udo Krieger has a question. I'm sorry. Professor Krieger, please.
Professor Carrera, thank you. I have one question regarding the complexity of management. What is the perspective on that? We have seen that autonomous computing and autonomous networking is an approach in that direction. What this perspective you didn't mention, that we apply self-learning controllers, and Academy of Sciences Lab 38 that I have been collaborating with has studied the origin of controllers in the early days with Zipkin and Zipkin's control principles. What we can do now to enhance these control elements by means of the challenges that we see with respect to the management of the RAN or ORAN without the intervention of people, that controllers can update their knowledge by means of data analytics and so on and so forth. Where is the perspective on this item?
Thank you. I agree with you. I mean, that's definitely, we cannot talk about everything, obviously, but that is definitely one of the means, one of the ways to progress in this area. Because again, since we are going to have access to huge amounts of data, this enables the networks to start being self-managed in a way.
Yes.
The self-management of networks is something that has been discussed for a number of years, and now I think it's becoming closer to reality, because now we have the means and the tools for this, what we can call again the self-management of the networks. On the one hand, we have the availability of data to take decisions, and we don't need, let's say, human hints on this matter. And now, and on the other hand, of course, we have also the tools of processing tools, of course, on all the stuff that has to do with artificial intelligence, connected with the control aspects to do this. So I fully agree with you. Yes, this will definitely play a role in the near future.
Thank you very much.
Yes, okay. Thank you very much. Now I really can't see other hands. Thank you very much, Lewis. And we do think about next year and about invitation to all of speakers and to you for our conferences. Thank you very much. Our compliments to you.
Thank you very much for the invitation again. My apologies for taking a little bit longer time in the talk, but I got enthusiastic speaking, so I'm sorry about that. Thank you for the invitation. It was a pleasure, and I hope we'll see each other in the near future. Thank you. Thank you. Bye-bye.
Thank you. Bye. Bye. And so we are moving along our plenary session. Next presentation will be made by Professor János Strik from University of Debrecen, Hungary. Please introduce yourself and you can start. Thank you very much.
Thank you very much. I hope you can hear me and you can see me. Yes?
You, but not presentation yet.
Yes. I just wanted to know whether the technical conditions are ready or not. So I will share my screen.
Yes, please.
And hopefully you should see my first slide of my
Everything
presentation.
is okay. Thank you very much. You can start.
Okay. First of all, I would like to thank for the invitation. I must tell you in advance that my lecture is not so general as Professor Correia. It is mainly devoted to the queuing theory and its applications. And again, thanks for the invitation, because Hungary is a very small country, and the people who deals with the queuing theory or the technical things is much less than in either in Russia or the other countries. So it is in the title you can see only my name, but it is this work and results is not only mine, but there are also other people. I don't want to enlist them all. I didn't want to forget anybody. So it is the outline on my presentation. The first, I would like to introduce the final source retry queuing system with collisions, because it is not clear for everybody. And then I will introduce and define the performance measures. And then the main part is how can we get these performance measures. I will introduce you to supported algorithmic and simulation approaches as in general, and mentioning the possibilities. The mathematical treatment of this presentation will be devoted to the asymptotic method, and then I will give you some comparisons. And finally, I will show some bibliography, only the main bibliographies, because since it is a review, it will have many publications. So let's see what is a final source retry queuing system with collision. It is a very general one. To understand it in detail, I would introduce the very first one, finite source queuing system. Finite source queuing system without retrier, without collision, without anything, just a finite source queuing system. If you see the books about queuing systems, these systems are mainly infinite source system, but no, it is finite source system. Let's see very early example for finite source system, and these systems were, how to say, examined independently of the, let's see, by the Russian or Soviet mathematicians and the Western world, Swedish, German, Hungarian, British, and so on and so on. But this common problem is related as machine interference problem. So that is an important and easy to understand queuing problem. So let's formulate the machine interference problem. Let's assume that we have n machines which are operating independently of each other, and after a certain time, a random time, they break down. They need service. The service and repair or fixing is carried out by a single or multiple repairmen. So these will be the servers. And in this, of course, these repair time or service times are random variables. After being repaired, these all machines start operating again. So this is a cycle system, and each machine is operating, waiting, under service, and after service, it starts operating again. So this is the basic and very simple model, and we assume that the service discipline is FIFO. And we didn't speak about the assumption about the so-called operating time, and we didn't speak about the so-called repair time or service time. These assumptions made the system very complicated because if we have exponentially distributed service time, not exponentially distributed operating time, and generally distributed service time, this system became quite complicated, and this model is called Takács model. Lajos Takács is a well-known Hungarian mathematician or engineer who left Hungary in the 50s and went to the United States, and he is the author, one of the Bibles of the queuing theory, Introduction Queuing, and it was mentioned. This machine interference problem was mentioned in his book, and then we can see some mathematical words about this mathematical model, but it is mainly for theory. But at the 60s, when the computers arrived, instead of machines, we can speak about terminals. And instead of repairmen, we can speak about central processor units. And instead of FIFO, service discipline, we can speak about different priorities, or later on processor sharing, or random, and so on and so on. So the simple model became complicated. One of the book Priority Queues, JSOL, some part is devoted to this finite source. And also there is a well-known book of Hideaki Takaji. He is a queuing theory and queuing system. He wrote 3-volume book, and one book is devoted to the finite source queuing system. Now let's see what happens if we have retrial queuing system, but without collision. Retrial queuing system means that there is no queuing instead of the service, but when a customer arrives and see the server busy, it goes to a so-called orbit. And the orbit, after a random time, it retries a try to get service. So the main difference between the traditional queuing system and the retrial queuing system, that in the case of retrial queuing system, the server can be idle, even there are customers in the orbit. So the utilization of the server is not as high as in the other service disciplines. But this retrial queuing system became very important in the communications. And if we see the publications, mainly the publications is due to the or arise from the infinite source. But now we have finite source, and a much less publication. You can find much less publications on it. Now let's generalize. This system, and we may assume that the server is not reliable. So we can say that in this picture, we assume that the source time are exponentially distributed, and if we have n sources, the parameter is lambda over n. It is just technical. It could be lambda, but it's denoted by lambda over n because of the asymptotic approach. So we have exponentially distributed source times, and the source generate request. And we see whether the server busy or idle, but at the same time we should see whether the server is able to serve or not, failed or up. And here there is a decision. If the server is available and it is idle, these requests go to the server, and the service time in the general case is generally distributed, and the distribution is denoted by B of x. And assume that during the service, the server doesn't break, and this service continues. But it may happen that during the service, the server break. And here it is just again a notation. We assume that the so-called uptimes, or the operating time or uptime of the server, is exponentially distributed, and the parameter of the exponentially distributed time is gamma sub 0 if the server is idle, and gamma sub 1 if the server is busy. So we can differentiate between the failure rate depending on whether the server is idle or busy. And of course, these rates could be 0, for example, if the server may break if it is busy. That case, gamma sub 0 is 0. So we can see that during the service, the server break down. And then again, we have different options. What happened with the interrupted service? There are different scenarios. The most, the most natural one is that the service continues, but there are many situations when the server restarts. And in the case of retrial queuing system, this customer goes to the orbits. No queuing, it is just simple, goes to the orbit. But it could stay at the server as well. It could, but it is different scenarios. Now let's see what happens if we have collisions. So we have retrials and collisions. The main problem with the collision, let's assume that the server is busy, so up, and service request. A new customer arrives either from the source or either from the orbit. And what is the collision? The collision means that the service stops, and both customers, the arriving customers and the customer which was under service, goes to the orbit. So the service is interrupted, and these two customers, the newly arrival one and which was under service, goes to the orbit. That is the new, that is the system with collision. And if you see the literature and if you see who deals with collision, not so many people deals with collision, and especially finite source retrial queuing system with collisions. It is rare, very, very rare. How can we get the idea? About 5 or 6 years ago, I read papers from the Tomsk Research University. This research group is led by Professor Nazarov. So I saw some papers, and then I wrote an email to Professor Nazarov to start cooperation with our method and their methods. They are experts in asymptotic methods, and we have some experience with the other methods. So we started the cooperation with, let's say, the Tomsk researchers, and then from that time we start investigations of a system with collisions. So that is the general case, and if you see here, we assume that the so-called retrial time is also exponentially distributed, and here if the server is busy when a customer from the orbit arrives, it will return. So there is no service. The service can start if the server is up and the customer may arrive from the source, either the source or from the orbit. And then it is this service is interrupted many times. The service is interrupted if the server fails, and the service is interrupted if a new customer arrives. So the service time is will be the total time, the total service time, in which we can calculate all the interrupted service times or the last service time, which is the so-called successful service time, which is it needs also investigations. Now let's see how can we deal with kind of problems. What are the performance measures? Which are the main performance measures of the system? Of course, the distribution of number of requests in the system. In the system, which means this customer can be in the service or in the orbit. Many times we deal with only in the case of retrial queuing system, we have to know the state of the server, whether the server is busy or idle. But in the case of a reliable or unreliable case, we have to know whether the server is up or down. And of course, we have to know the number of customers in the orbit. So that is the first step. A much more complicated task is to get the distribution of number of retrials. So as I mentioned customer arrives, if the server is busy, it goes to the orbit. From the orbit, it tries. If the server is busy, it returns, but it can return to the orbit. In that case, if there is a collision or there is a service failure. So to get the distribution of number of retrials, it is very, very complicated. I didn't see any papers concerning to the exact distribution, only asymptotic. Exact, I couldn't see. And of course, not only the distribution of number of retrials, but distribution of the response or waiting time of a customer. These are very, very complicated. And here we can use only, as far as I know, we know only asymptotic results. Now, how can we get these results? And how can we check whether our approach or our model operates well or not? The easier part is to use the so-called tool-supported methods, which means we can use different softwares, and one of them is a MOSEL, which is Modeling, Specification, and Evaluation Language, and it was developed at University of Erlangen. And Professor Udo Krieger, we met many times, and he knows this MOSEL. The other, and only a few users of MOSEL, if we see the literature, the people from Erlangen, they didn't use, and the other research center uses their own methods. But we learned this, and we like this MOSEL, and still we use it. The other one is the algorithmic method. We can realize that to get exact and calculable results nowadays in analytical modeling is very complicated. It is very rare if we can have exact results. That's why we have to use the algorithmic method. Even the book of Alterejo, which is the Bible of the retrial queuing system, it is mentioned that is algorithmic approach to get. And here, the next one, when this tool-supported or algorithmic method doesn't helps, the simulation approaches. Myself, first in the earlier times, I didn't like the simulation approach because since it is not a big mathematical, from mathematical point of view, it is not so complicated because there is no tricks, there is no ideas and so on. But later I realized to write a good simulation program, which is fast enough, it is not so easy, and it depends on many factors. Which language do you use, and so on and so on. But recently we used the simulation. We wrote our simulation programs because we realized that if we have a ready-made, it doesn't help. We use C++, and using simulation, we try to get the effect of distribution of the involved random variables and the distribution of number of customers. So if we assume the source times are not exponentially distributed, what happens? How the distribution of the source time affect the main performance measure? There is a big difference between if we have Erlang, hypo-exponential, for example, then the gamma or Pareto. What is the effect? What is the main factors? So the next one, the effect of this involved random variables and the mean and variance of the response time. So not the number of customers, but the response time. And finally, the same question for the number of retrials. So let's see now the asymptotic. Methods for different cases and different assumptions. We have quite a lot of publication concerning simulation. But no, since mathematical point of view, these asymptotic methods is more interesting, and I think it is more important. I would like to devote the time to this method. And now we will use the following notation and the following assumptions. We will have n sources, and these each of the sources generate requests for an exponentially distributed time, and the parameter is lambda over n. Lambda over n. That will be this divided by n. That will be some kind of scaling. We have retrial queuing system, and the service time is assumed to be exponentially distributed with parameter mu. However, this server is not reliable, and it may break down. We assume that the operating time or the uptime, the server is exponentially distributed if the server is idle. If the server is busy, the the so-called failure rate is gamma sub 1. But no matter whether this failure happens in idle or busy state, the so-called fixing time or repair time is exponentially distributed with parameter gamma sub 2. We will have collisions. So if the server is is busy with servicing, a new customer arrives, this customer goes to the orbit, and from the orbit they retry after an exponentially distributed time, and the parameter is sigma over capital N. N is again a scaling factor. We must mention that what happened with the request generation if the server is down. There are different options. We deal that options that the request generation from the source continues, and these requests arrives into the system, but immediately goes to the orbit. And now we have to deal with what happens if the server fails when it's servicing a request. We assume that this request goes to the orbit. So this orbit collects. Or of course, we can treat different cases. These requests can stay at the service, and it can repeat or resume. There are different assumptions, and not assumptions, but scenarios and protocols. But in this case, if the server is failed, the customer goes immediately to the orbit, and if the server fails, the interrupted request goes to the orbit again. And now we are interested in how can we get the distribution, the steady state distribution, the number of customers in the system. In the system means either here in the service or in the orbit. For that, we have the so-called asymptotic results for the first order. So we have exponentially distributed search time. I gave you the parameters. Exponentially distributed service time, single server, infinite capacity, and the number of sources is capital N. So that is the first result. But I will show you here that that is in other words, it is the characteristic function. The main advantage is that when we are interested in what is kappa 1, how can we kappa 1? We have to solve these equations where we have these quantities. The main the main result is that everything can be calculated after giving the parameters. Each are all well-known parameters, but it is only the first order. What about the second order? For the second order, if we see this, all these, I just want to show why we need these formulas. We would like to approximate the number of customers in the system by a normal distribution. for which we have all exact parameters. We can get, it is not nice formulas, just you have to know that we have a parameter, we have a kappa 1 and kappa 2, and these how to say, parameters can be obtained by the help of the input parameters. So that is the asymptotic of the second order. And here, that is the corollary, we will use the distribution of number of customers in the system is Gaussian, that is normal, and the mean is, that is the number of sources, capital N, kappa sub 1 and kappa sub 2, where kappa sub 1 and kappa sub 2 can be obtained explicitly. That is the nice result. So the next one, how can we get the distribution of the response time or surgeon time? How can we get the distribution here? That is the limit theorem for the normalized distribution, which is the so-called generalized exponential distribution. For the Q, we have again the kappa, sigma, and so on, and so on, and so on. So, and here we see. That is the characteristic function, which means in other words, that is the generalized exponential distribution. The next important result is how can we get the number of transitions or the number of retries of a customer? And it appears it is geometric. And the parameter of the geometric is this Q. And the result, here you can see the result. It is, the Q is given, and for Q we have A was defined before, kappa sub 1 was defined, and it is geometric. Now let's see some comparison. Why we need these asymptotic results, and how can we see the goodness, not the goodness, but how effective these asymptotic results are? Because many times for this distribution, number of retries, distribution of the response time for exact cases only very rare, and I couldn't see any exact results for these systems. That is the mean waiting time. And in the book of Fallin, about retrial queuing system, there is an interesting unexpected phenomenon that increasing the arrival rate, the mean waiting time has a maximum. I couldn't see any explanation why it happens. It is just how to say, a notice that we realized in that, but not in all cases. In all cases, generally not. But there are some parameters. We have some parameters when it happens, and we just, how to say, reproduce this maximum phenomenon. It is without collision, and the number of sources is 10. Now let's see what happens with collisions. With collision, of course, the mean waiting time should be greater because the collision interrupt. And here we see that is almost 55 with collision, and what happens? It is only 35, but with only specific parameter setup. Now let's see how can we see how effective asymptotic method is. That's why we can compare the numerical results which were obtained by the Mosel with the same, and you can see here the input parameters, different failure rates, that is the repair rate, and these are the sigma, mu, and so on and so on. And we can see it is the distribution when we have n, that is again the number of sources, 15. You can see these are different. These are the solid, these are the exact. That is the asymptotic. We may expect that if we increase the number of sources, they will be closer and closer. It is the case when the source numbers are 50. You see? Almost the same. It should be normal. But it is for the distribution of the number of customers. That is we don't speak about the distribution of number of retrials, and we don't speak about the distribution of the response time. But these will be all consequences of this, because if they are close, all the others are consequences. Now, how can we compare how the exact and asymptotic results are close enough? That is the asymptotic waiting time in the order is different. No, that's why to measure the closeness of the exact and asymptotic distribution, it is not new. We introduce the Kolmogorov distance. That is the Kolmogorov distance, and we had simulation results, and also we have numerical results, and we have asymptotic results. Of course, the simulation can run in most cases, even we don't have numerical results. The simulation operates. So in this case, we use the simulation. The input parameters are here, and we assume that here gamma is the same. So there is no difference between the failures, whether the server is idle or busy. It is the same. So let's see the results. These are the Kolmogorov results. These are the failure rates, and these are the number of sources, and we may assume that if n, the number of sources increasing, the Kolmogorov distance should decrease. See, it is the Kolmogorov distance. Decrease. No, it is another case. It should be different. It's different, but the Kolmogorov distance always decreases. So here, these results are devoted to the exponentially distributed service time. The next step, what happens if the service time is arbitrarily distributed, generally distributed? These are the latest results, and I didn't want to show the formulas, because of course in this case the formulas are more complicated. Who are interested in what happens if we have generally distributed, I will show you the publications and also all the results which are connected to our investigation can be found in my homepage, and I will show you homepage again. It was in my opening slide, but I will show you, and you can download these papers. Now let's see what what are our current investigation, and at the same time it is our future investigations. So far we assumed that a customer can stay in the orbit. There is no restriction how long it should stay, for any time. It's no restriction. But many times, the customers are impatient. And it may happen that after a time, you say, for example, it could be a constant, whom would say, I don't have time to deal with, to wait, and it returns to the orbit, returns to the source without any service. So in the case of impatience, there will be customers who will be served successfully. These are the successful service. But of course, there will be many customers who, due to the impatience, they return to the source without any service, without finishing the service. I wouldn't say that without any service, because it may happen that it went to the server. The service starts. But due to the failure or collision, it returns to the orbit. And in the orbit, we add all the times he spent in the orbit. You understand? The total time of a customer spent in the orbit. It is again, it is not an easy job. I looked for the literature. There is no any result concerning this type of system. No, it is new, but of course, if we don't have collision, and if we don't have breakdown, we can deal with queuing system with impatient customer. There are papers, but there is no papers with collection and breakdown. And of course, here, one of the most important performance measure is what is the probability that a customer will leave the orbit or the system without a successful service. It is one of the main important measures. And we dealt in the last 2 years, we treated this kind of system. We treated if these source time are exponentially distributed, the orbit time or retrial times exponentially distributed, service times are exponentially distributed. That case, we could model it by the help of Mosel. But as soon as we have non-exponentially distributed time, that case we could do or we could investigate only using simulation with non-exponentially distributed service time, non-exponentially distributed orbit time, non-exponentially distributed service time. That case, we could see what is the effect of the distribution. For example, the probability leaving the orbit without service, without a successful service. We could see the effect of the distribution, and we have different papers on it. We had different papers in it, and we could participate, for example, in the DCC conferences in the last 2 years, ITMM conferences on this kind of topics. And the latest, which you will hear in Wednesday, when our group will introduce, not with impatience, but the so-called catastrophes. The catastrophes means that instead of failure of the server, in case of catastrophe, all the customers from the orbit and the customer in the service will go to the source. That is the catastrophe. We started the investigation with using Mosel, because Mosel helped us to check whether the simulation program operates well or not, because if we have exponentially distributed time, the simulation should give almost the same results as the Mosel. But the Mosel works only for exponentially, and it is a constraint. And that's why we need the simulation. So in conclusion, we dealt with only the highlights. Of course, we have more paper. It is only the highlights. Final source retrial queuing system with collision, different solution approaches. I mainly devoted to asymptotic results. Recent non-reliable with collision using asymptotic, and finally I gave you some graphical illustrations and comparisons. Now let's see the bibliography of our results. The latest one, it is a very good review. This book is, edited by Vladimir Vladislav Anisimov and one of the French colleagues. And it is recent results in final source retrial queues with collisions. You can get this chapter because it is the 8th chapter. You can download this 8th chapter from my lecture note, from my homepage. It is among the book. I will show you my homepage. You can get it and you will see all the references and more detailed results that I could show you. Let's see the papers. These papers, the result, what I showed you, the result of this paper, that is the MM1, and it is about the distribution of the number of customers. It was published in the Annals of Operation Research 2 years ago. And then if we are interested in the sojourn time or response time of this exponentially distributed system, it was published again in the Annals of Operation Research 1 year later. Let's see what is the situation when we have generally distributed service time. This was published just recently. It is in methodology and computing in applied probability. I could give you only the DOI because it is open source and the published or printed version hasn't published yet. It wasn't published. What is the situation when we are interested in the distribution of the sojourn time? It was submitted to the publication Mathematica journal. And that's all I wanted to tell you. And I prepared for the questions again. And finally, as I promised you, here I give you my homepage. It is my homepage. And you can, I also can show you this one. Hopefully you can see it. Yes, you can see it. And here, if you see the books, in the books, here, that is the these recent results in finance. So just go there and you can download the paper. And also, I don't know the reason, but the French, I don't know, they got financial support, and all this book, it has 2 volumes, and these books were translated into French as well. So here you can download, And if we go back to the papers, in the papers, here you can see in the the papers here, and it is not big enough. Here you can see everything, and not only see, but you can download all the results, all the papers, all the results. And if somebody have questions, request, anything, just write me an email and we are ready to answer. And once again, I am very grateful to the organizer that gave me the opportunity to show the results of our research group in Debrecen, the second largest city in Hungary, who doesn't know it. Not a big, Hungary is a very small country, only 10 millions, but the Hungarian mathematicians try to do our best to give some contribution to the queuing theory and the science. Thank you very much.
Okay, thank you very much, Professor Strick. Question, please. Question, please. No question. Thank you very much.
Okay, thank you very much.
Last minute, one question. Who is it? Professor Petrov, please.
On your microphone.
No question. Thank you very much, Professor.
Okay, thank you. Thank you.
Now I invite Professor Trivedi from Duke University, United States of America.
Okay. So do I start, or is there an introduction or anything like that, or what? Hello? Can you hear me?
Yes, we hear you, Kishore.
Okay, so shall I start, or there is any introduction? That was the question. And where is the slide share?
You can start.
How do I share my slides? Is there a button somewhere? I've used Zoom more than. Where's the slide share?
Share content button.
Sir, next to the camera, you can find up arrow.
Yeah.
Next to the camera? Okay, up arrow. Okay.
Up arrow. You kindly click the up arrow, then you will get the folders.
Okay,
Yeah.
I got it.
Okay.
Doesn't let me share it yet, so you need to allow me to share. Dharma, good to see you. How are you?
Yes, sir. Fine, sir. Nice to see you. I gave a talk in the morning and I told about you about the stochastic modeling.
All right.
Yes. So I have all the audience for you.
Somebody has to give me permission to share. It's circling. It's not doing anything.
It is already shared. It is already shared, sir. No?
Отключить меня.
It's not working somehow.
Just reload, Kishore, and then go to the full screen or use PDF, whatever you have.
Okay. Now it's in the cycle mode. It's cycling through, doing nothing. Restart the program. Okay. Team is restarting.
This is what software engineering is very important.
works this time. In the meantime, is there a joke or something? Because, well, at least I can say namaste and good morning. It's still cycling, is it? Ah. We can't access your content.
Would you like please to increase your slides?
I
Please
did that already. Let me
increase
try
your
again.
slides.
Come on, man. I have not had this kind of a problem before.
Professor, you click again that same up arrow, then you include the file, the PPT file. Your audio and video is fine. Only the presentation slide is giving you trouble.
I know. But so I've been trying that and it's not working.
Yeah, so now you click the up arrow.
Again?
Yes, then you go to the full view mode.
Please.
Okay, it's enough, I think. That's enough, please.
Yes.
Okay.
Yes, sir. Now you are ready. Correct.
Okay, display settings.
Click the buttons. We are ready.
Okay, can you see it now?
Yes, sir. Yes, sir. Perfectly fine.
Okay, so good morning, and today I'm talking about something very different from what was in the previous talk by Professor Janos. I'm talking about software fault tolerance via environmental diversity. And recently I learned from one of the Air Force bases that they like to put the bluff in the front, bottom line up front. What is it that my overall goal is in this talk? And so my main point is that today's complex systems, whether you talk about software-defined networks, cyber physical systems, smart grid, aircraft, spacecraft, weapon systems, IoT, whatever, they end up containing a huge amount of software, which almost naturally means that the software is a major cause of system undependability. And therefore, software failures during operation are a fact that we need to learn to deal with. And traditional methods of software fault tolerance, which we'll briefly describe based on what is called design diversity, is found to be expensive and hence does not get used extensively in practice, except in life-critical systems. So what we are proposing is relatively newer idea, software fault tolerance based on what we call environmental diversity, which is relatively inexpensive, and that should be exploited more. And another way to look at it is that in the software engineering community, so far, they have concentrated on finding and fixing software faults or bugs. We should continue to do that. However, we need to also pay equal attention to failures caused by these bugs and the recovery from these failures during the operational phase. And I believe a lot more attention needs to be paid to this aspect. Another way to put it is that software reliability engineering community so far has been devoted entirely to software reliability. We need to pay attention to software availability as well during operation. So that's the overall picture, and I'll try to paint details of this picture now for you. And the overall presentation is divided into first motivation definitions. Then I will motivate the rest of the presentation by means of a real system example that I had an occasion to deal with that will lead us to a new classification of software faults. And finally, that will allow us to define what we mean by environmental diversity. And I will briefly mention different methods of mitigation of faults and failures, and then conclude. It is very clear that today we depend on computer and communication systems for just about everything we do in our life. And therefore, we expect these systems to be highly dependable. Now, the word reliability is often used in a generic sense as an umbrella term, but it is also a precisely defined mathematical function. In order to remove the confusion, one of the working group of IFIP working group 10.4 proposed dependability as an umbrella term, and reliability is then used as a well-defined mathematical function. Given this background, dependability, the umbrella term, has been defined as the trustworthiness of a system such that reliance can justifiably be placed on the service it delivers. And then they proposed a dependability tree with 3 branches to begin with, namely attributes of dependability, means to achieve dependability, and threats to dependability. So with respect to attributes, they define reliability, availability, safety, and maintainability as the 4 attributes of dependability. Then they talked about means to achieve dependability: fault prevention or fault avoidance, fault removal, fault tolerance, and fault forecasting. We're going to concentrate primarily on fault tolerance in this talk. And the threats to dependability are classified into 3 things: faults, errors, and failures. We will go through that in a little bit more detail. So what dependability theory and practice wants to avoid accidents like this that have happened. And in order to go further, we need to be very, very clear on the terms faults, errors, and failures. Now, different groups define this differently, but we should be very clear the distinction between them, whatever definitions we choose. And oftentimes, because of not very clearly defining these terms, confusion arises. So failure occurs when the delivered service no longer complies with the desired service or expected service. And error is that part of the system state that may lead to subsequent failure. And the real cause of all this is a bug that may be there in your software. So a bug or fault by itself is not a problem. Only when exercised by the appropriate set of inputs, it may give rise to some wrong bits in your internal state of the system. And those bits by themselves is not a problem, wrong bits, unless and until they propagate to give a wrong answer or no answer. That will be a failure. So fault may give rise to error, which may give rise to a failure. And this can be further solidified by this simple picture. Fault by itself, when exercised by the right set of inputs, may have a wrong bit internally, and that may propagate to give a wrong answer or no answer. With that initial definition, there is also the notion of fault latency. From the fault occurrence until the error occurrence, the fault is dormant until then. So this is called fault dormancy, and error occurrence to the failure occurrence is called error latency. Now, there are situations in which there may be very long fault dormancy. For example, there's a very often quoted example in the software reliability literature where there was a bug in Therac 25 system introduced in 1982, and the first error occurred in 1986. So it is possible for a very, very long fault dormancy. And similarly, it is also possible from the first error occurrence until failure, there may be very, very long latency, error latency. And this particularly occurs, as we'll see in a little while, under the software aging phenomena. Faults may be classified further into physical versus design, manufacturing, integration versus interaction faults. Faults may be classified into hardware, software, or human faults. We are concentrating in this talk on software faults. Faults may be also classified into node faults, link faults, malicious and non-malicious faults. In the hardware context, they may be classified further into permanent, intermittent, and transient. And in the software context, and this will be we'll be going through in more detail, into Bohr bugs and Mendel bugs, and also aging-related bugs and so on. Failures can also be classified into so-called omission failures. That is, you don't get a response when you are expecting a response from your system. It may be because system has crashed, or in your program there's an infinite loop. Second kind of failure is a value failure. You get a response, but the answer is wrong. And yet another kind of failure is a timing failure. You get an answer, you get a right answer, but the answer may be too late. And such failures are often called performance failures or dynamic failures. And in principle, it is also possible to have an early response as wrong as a timing failure. Failure effects may be classified into safe versus unsafe failure, and benign versus catastrophic failures. In the context of security, they may be classified into breach of confidentiality, breach of integrity, or loss of use. Now, can we trust our computers in general? And the answer is clearly no, that there are lots and lots of failures that occur all the time in practice. This is some list that is easily obtained. There are many others in very famous high-tech companies like Amazon, Google, Microsoft, Facebook, and the list goes on. And furthermore, what we find is that the amount of software in systems is increasing by leaps and bounds, exponentially more or less. Therefore, the failures are more and more due to software rather than hardware. And so you might say that hardware fault tolerance, hardware fault management, redundancy management, reliability and availability modeling are relatively well developed. But the problems in practice are more and more due to software faults. Therefore, the key challenge for overall system reliability or dependability is that software is one of the weakest links in developing highly reliable, highly available systems. And quite often in practice, people assume software is failure-free in claiming 5 nines and 6 nines availability in practice, which is really ridiculous. And we can corroborate this, the fact that software is the main cause. This is borrowed from one of my friends at Alcatel-Lucent that shows that in their overall downtime breakdown, hardware contributed only 13%, whereas software contributed 65%, and procedural or human contribution was 22%. So we should be concentrating on software faults and failures rather than hardware faults and failures. And once again, you go back to Google and Amazon, due to software problems, you see the downtime in these famous examples. And there are many, many more such examples that most advanced tech companies are not offering highly reliable software. So we want to also consider the most recent examples. One Fastly customer triggered internet meltdown on June 9. And of course, there is this famous commercial aircraft Boeing 737 software problem where people died. So it is very clear now that we need to worry a lot more about how to build more reliable software. And such failures and downtime due to failures may lead to loss of reputation of the company that produces these products, may lead to loss of revenue for these companies, and may lead to possible loss of mission, and finally may lead to possible loss of life, as we saw in Boeing 737 MAX problem. So what we need to do is develop methods that reduce system failures and reduce downtime due to these failures, which may be contributed by hardware, software, or human beings. And then we need to also develop system reliability and availability assessment and bottleneck detection methods for assessing whether we are doing well or we need to do better and how to do better. For the second part is what I normally talk about, but today I'm not going to talk about that. I'll simply refer you to a recent book that I published with Andrea Bobbio in Cambridge University Press. That is really the state of the art on this topic, second topic, reliability and availability assessment and bottleneck detection. And this is what the book looks like. And popularly, we are calling it Green Book because it has a green cover. But my concentration today is on the first topic here, namely how to reduce system failures and reduce downtime due to these failures, which may be contributed primarily by software, is what we are considering in this talk. So methods to improve software reliability and availability. The first idea would be fault avoidance or fault prevention. Second idea would be fault removal by testing and debugging. Third idea will be fault tolerance or use of redundancy. And fourth idea would be fault and failure forecasting to help you improve system reliability and availability. So very briefly, first means fault prevention or fault avoidance. The idea is that you want to build software that has very few bugs to begin with. Now, in order to do that, there are good software engineering practices, and there is a lot of literature on this topic. There is also the notion of developing a good software architecture. Again, there is a lot of literature on this topic. I will not go into. The third idea is to use formal methods. And formal methods might mean using formal languages such as UML, SysML, BPML, trying to do proof of correctness of your program. And third idea is model checking. And there are a number of tools for model checking that are available today that are fairly effective. But in spite of all this, we may try all this, people have been trying all this, bug-free code not yet possible for large-scale software systems. That is a reality. And I don't know how long this will remain, but it is true today that we are not able to produce code, large-scale software systems that are bug-free, in spite of all these techniques. And yet we have very strong need for failure-free system operation. Software systems have many bugs, and yet we want failure-free operation of the system. And so the next idea is to do fault removal by testing and debugging. And there are many different, and this can be carried out at the specification design phase, development phase, operational phase. And there are many tools available to try to help in this process, and many different techniques available, including this something called combinatorial testing and so on. But once again, and of course, during this time, if you are doing testing, if you keep track of times between failures, then it is possible to parameterize a so-called software reliability growth model, which will allow you to predict whether you have done enough testing or do you need to continue testing and for how long. And much of software reliability engineering is filled with literature on this topic, software reliability growth modeling. But it is very clear that it's impossible to fully test and verify if the software is fault-free. And there's a famous quote by Edgar Dijkstra on this. And software is still delivered with many bugs, either because of inadequate budget for testing, very difficult to reproduce, detect, localize, correct bugs, or inadequacy of techniques employed, known, and so on. For whatever reason, in practice, the code that is delivered, that is in operation, has many bugs, as we all have experienced. The next, so what we can summarize so far is that today's complex systems contain a large amount of software, Software in operation contain a lot of bugs in spite of best fault avoidance and fault testing removal techniques. And software failures are a major cause of system undependability. Therefore, the next idea would be to use redundancy in the case of software. Software fault tolerance is a potential solution to improve software reliability in lieu of virtually impossible fault-free software. For traditional software fault tolerance, the idea was that the things that are employed in hardware cannot be employed in software. In hardware, we use statistically identical copies as a form of redundancy. But they thought that this will not work in software because, say, 2 copies of software will have exactly the same bugs. So if one copy fails, the second copy is guaranteed to fail. So they came up with the notion of design diversity. So you give the same specification to different teams of software developers, encourage them to use a different algorithm, different language, different development system, different testing techniques, so that multiple versions, diverse versions produced by these different teams are likely not to have the same kind of bugs. So they will not fail on the, more likely not fail on the same set of inputs all the time. Use of multiple versions of variants of software was the standard method for software fault tolerance advocated all along in practice and in academia in the literature. And so different versions may execute concurrently or sequentially. And the rationale is that multiple diverse versions will fail differently for different inputs or workloads. And multiple versions are developed from common specifications. Also helps with respect to intrusion tolerance. We will not get into that. So the classical techniques based on design diversity, there are 2 principal methods that have been developed since the 1970s called recovery block and inversion programming. And key references for this I'm providing to you. The first 2 are references about recovery block, and they came from Brian Randall's group at the University of Newcastle upon Tyne. And the second idea of inversion programming came from Al Levisian's group at UCLA. And so they have a lot of literature on this topic. But what we find is that these notions that have been around since 70s are not used very much except in the life critical or safety critical systems. So design diversity is found to be too expensive and used only in safety critical applications. And yet stringent requirements for failure-free operation in non-safety critical applications do exist. So what we have a challenge then on our hands is to provide software fault tolerance that is affordable. That is something that we can live with. And so our answer to this is what we call environmental diversity as opposed to design diversity. And so what we have covered so far very quickly is that fault avoidance or fault prevention using good software engineering practices, formal methods, and fault removal by testing or debugging, and then correspondingly software reliability growth models. We have talked about fault tolerance via design diversity, and now we are entering the notion of environmental diversity. We will later very briefly mention fault failure forecasting. So in order to motivate environmental diversity, I will take you to a real system example that I was asked to analyze in around 2007. And this is a system that IBM developed for session initiation protocol on top of WebSphere. And they asked me to analyze this system for its reliability and availability. I'm not going to get into the analysis there, but I want to show you the design of the system very briefly. So this is a high availability SIP system where real system developed by IBM. SIP stands for Session Initiation Protocol, which is used normally for voice over IP. In fact, today most every system of telephony uses this. And the hardware platform that they had used was IBM Blade Center, and software platform they had used was the IBM WebSphere. And the telco customer asked IBM for models to quantify this product. And IBM asked me to lead the modeling project, and we did in fact did a very detailed system availability analysis, which is published in a very nice paper in conference called PRDC. And we also did what they call reliability analysis, very interesting way of computing the number of dropped calls due to failures. And this was also published in a conference and subsequently in a journal article too. That's not the point I want to make now. I want to show you the architecture of the system. And the architecture of the system is shown in this block diagram. So the system consisted of two blade center chassis, chassis 1 and chassis 2. And each chassis had 4 blades, 1, 2, 3, and 4 blades. And each blade has an operating system called Linux. And apart from the operating system, there are 2 application software that system has. One is called proxy, SIP proxy, and the other is called application server or WebSphere application server. They employ 2 copies of the SIP proxy and 12 copies of the application server. And furthermore, an application server in one chassis is paired with an application server in the other chassis, so that when this application server fails, all the work will be taken over by the pair in the other chassis. So this particular system then, hardware configuration wise, had 2 blade center chassis, 4 blades on each chassis. And they told me that one chassis would be sufficient from the performance perspective, from the throughput perspective. So they employed 2 chassis for fault tolerance. Software configuration wise, there were 2, as you saw, 2 copies of SIP proxy. And they once again told me that one SIP proxy would be enough from the throughput requirement, but they employ 2 SIP proxies for redundancy. Similarly, 12 copies of WebSphere application server are used, although 6 would be enough from the performance or the throughput perspective. So once again, there is redundancy in the context of app server. And furthermore, I already told you that each WAS instance forms a redundancy pair or a replication domain, which was installed in another node on a different chassis. So the fault tolerance that we have, system has both hardware redundancy and system has software redundancy. But the software redundancy is very different from what the literature tells you. Textbooks on software fault tolerance tell you that identical copies of SIP proxy are used, much like what we do in hardware. Identical copies of app servers are used, much like we do in hardware. They have exactly the same bugs. They're not diverse version. So types of redundancy, software redundancy used is not design diversity, which is what entire academic literature tells you, but the replication of identical software copies, the things that was warned against by the academia all this time, all these years. And then I asked them, what is the normal recovery after a failure due to software? And they said they use time redundancy. That is, they will restart the software. If that doesn't work, they will reboot the node. And if that doesn't work, they will fail over to a software replica in the other chassis. Only when all this fails, then actual repair of the software bug is invoked. So the question is then, that arose in my mind at that time, that retry, restart, and reboot are things that have been known to help with dealing with hardware transient faults. We have known these all along, but now they are being advocated in dealing with failures caused by software bugs without fixing those bugs. How do you expect after restarting the thing to work? Exactly the same bugs are there. if this should work, why? The real engineers in practice are using this. And I also saw in many other systems subsequently, the same ideas being used. Similarly, failover to an identical software replica that is not a diverse version, having exactly the same bugs. Why should that help? And if it is used like that, what is going on? If 30 years ago I proposed this in a conference, they will think I'm crazy and they will put me in a asylum. But today, these are being used very routinely. So the answer perhaps lies in the following, that not all bugs are equal. Fault triggers make the difference. Some bugs are trivial and failures caused by them can be easily reproduced once detected during testing. Other bugs are subtle and even reproducing failures caused by them is challenging. And this may be due to race conditions, memory leaks, hardware-software interaction. And these bugs have a significant impact in terms of software failures and the costs. So this leads to a classification of software bugs. Now, I don't see the people here and so on, so I'm not sure how to see if there are any questions. Show taskbar, maybe end slideshow. Anyway, let's continue. So, and now I want to remind you once again, the distinction between faults, errors, and failures. A fault is a bug in the program in the context of software, one or more bugs in the program, and that by itself is not a problem until and unless it is exercised by some inputs that may give rise to errors, which are wrong bits. And these wrong bits by themselves is not a problem until and unless a failure is produced at the output that is seen by the users of the software. And so our main theme now is that we submit that a software fault tolerance approach based on retry, restart, reboot, or failover to an identical software replica, which is not a diverse version, may work because of a significant number of software failures are caused by what we call Mendel bugs or environment-dependent bugs, as opposed to the traditional software bugs now known as Bohr bugs. So let me introduce you the notion of Bohr bugs and Mendel bugs. Next. This is the classification of software bugs that we have been advocating. So Bohr bug, which is abbreviated as BOH, is a bug that is easily isolated and that manifests consistently under a well-defined set of conditions because its activation and error propagation lack complexity. So under a given input workload, either this bug will exercise and produce a failure or not, exactly the same way every time. And I submit that this is the only mental model of software bug we have been having all this time. But we are now seeing bugs that are no longer behaving such deterministic behavior. So bug whose activation or error propagation are complex. Typically, Mendel bug is difficult to isolate and or failures caused by it are not systematically reproducible. So sometimes under the same workload, failure will occur and sometimes not. It behaves non-deterministically. And another bug that is very interesting, which we are not going to deal with, it's a separate topic and talk in itself, is called aging related bug, a bug that leads to accumulation of errors either inside the running application or in its system context environment, resulting in an increased failure rate and or degraded performance. So, we are going to concentrate mostly on this non-aging related Mendel bug. And Mendel bugs, besides workload and internal state of the software system, its system context or operating environment participates in determining whether a failure due to such a bug will occur. And so fault is a Mendel bug if its manifestation as a failure is subject to the following complexity factors. Long time lag between fault activation and failure appearance, that may be one. Operating environment dependence, operating system resources, other applications running concurrently, hardware, network, etc. may interact with the workload input to the software in order for it to become a failure. Timing among submitted operations might also affect whether a failure will occur or not. Sequencing or ordering of operations within your software may also determine whether a failure will occur or not. And a failure due to Mandelbug thus may not recur upon resubmission of the same workload if the operating environment has changed enough. And so we can then see that these Bohr bug and Mandelbugs are complementary antonyms, and aging related bug, which we are not discussing very much in this talk, is a subset of Mandelbugs. And now this is the theory. Now I need to prove the theory by some real data. So what we did is we decided to first explore data, problem reports from all NASA satellite onboard software, and we were able to go through the problem reports and determine the percentage of bugs of these three types. Then we went through Linux, MySQL, Apache, Axis, and HTTPD open source Bugzilla reports and did the similar kinds of analysis. And then we did the analysis on the Android operating system. And finally, one more detailed analysis of Linux. And we found that in the JPL NASA problem reports onboard software, we found that some 32% of bugs can be legitimately be called non-aging related Mandelbugs. Similar data is obtained in Linux, MySQL, etc. So we can say that Mandelbugs are a reality in actual operating software systems. And so we need to pay attention to the notion of Mandelbugs and the failures caused by these Mandelbugs. Android also is given here, and then finally Linux second time around with much more detailed reports and so on. So this is reality that Mandelbugs is something that we need to pay attention to. And so now this fault classification is not merely theoretical, it also has practical implications. And each type of software fault may require different type of approach during development, testing, as well as during operations. And so environmental diversity is now we are ready to talk about. And so basically, this is what happens, that a fault may be activated not only by the workload, but environmental factors may affect the activation of the fault into error and also propagation of error into failure. That is the difference between Bohr bug and Mandelbug. The fact that other factors besides the workload may affect the activation of the fault and to error and error into failure. So for a Mandelbug, environmental factors could affect the fault activation and error propagation. And examples are data race, deadlock kind of bugs whose fault activation could be affected by other concurrently running processes, threads. And so therefore, after a restart or reboot, we may not observe the failure again, even though the bug is not fixed in the system. Similarly, if memory leaks occur, whose error propagation could be influenced by the size of available memory and other programs running concurrently. So something called rejuvenation or reconfiguration may avoid or postpone the failures. So software fault tolerance, new thinking then, is what we call environmental diversity as opposed to the traditional design diversity. And our claim is that retry, restart, reboot, failover to identical software copy may well work since failures due to Mandelbugs are not negligible, 40% or some in Linux bug reports. We thus have an affordable software fault tolerance technique that we call environmental diversity. And now software is beginning to look more and more like hardware. Software is beginning to look more and more like hardware. So what is the environmental diversity? Basic idea is that restart an application without fixing the bug after recovery, and it most likely works. Why? Because the environment where the application executed in has changed enough to avoid fault activation. Environment is understood as the OS resources, other applications running concurrently and sharing the same resources, interleaving operations, concurrency or synchronization, and so on. And this is fault tolerance because we do not necessarily fix the bug. Fault caused a failure, but this failure is dealt with by using time redundancy. Hence, the user may not experience the failure again on retry. So what are the methods of mitigation very briefly? And this is the master chart. It has a lot condensed in it. So, and all software are subject to Bohr bugs and Mendel bugs, whether it's operating system itself, middleware, or applications. And so if Bohr bugs are there, and we see Bohr bugs all the time, we see Mendel bugs all the time. Bohr bugs are there, the best way to deal with them is to find and fix them during testing phase. But in spite of all the testing, the bugs remain. So the traditional method of dealing with Bohr bugs during operation is design diversity, and I briefly mentioned that. There's another idea called data diversity, which hasn't caught very much, but it is also possible. But when we talk about Mendel bugs, particularly non-aging related Mendel bugs, most common technique at operational time is retry, failover to standby, restart, or reboot. And these are applied after the occurrence of failure. So these are reactive techniques. Now, if you talk about aging related bug, which we didn't talk about very much, there is the notion of rejuvenation, software rejuvenation, which is a proactive technique for dealing with software bugs of this type, aging related bugs, which we didn't talk about very much. So the implication of Mendel bugs now is that we can measure model software availability during operation, not just reliability, because we are talking about recovery after software failure also. And we can therefore talk about combined software and hardware availability. But what we need to do further, a lot of research is needed to develop methods for debugging and testing for these very complex Mendel bugs or environment dependent bugs. We want to be able to determine the environmental factors that are responsible for manifesting these bugs. And can we do a runtime control of these environmental factors to avoid failure occurrences due to Mendel bugs? Can we talk about optimal recovery sequence after occurrence of failure? Can we use experimental methods to determine the nature of software failure times? And can we apply the methods that are well known in the hardware context, such as accelerated life testing in the context of software? All these are being researched, and there is a very fertile area for open research in the context of Mendel bugs. And we have investigated a little bit this reproducibility of Mendel bugs and conducted a set of experiments to study the environmental factors that affect the reproducibility of Mendel bugs in my school. And we found in that particular instance, disk usage, memory occupancy, and concurrency level are the three main factors that determine whether or not the bugs that we particularly talked about in that context become failures. And high usage levels of these environmental factors increases significantly failure occurrences due to Mendel bugs. And this is a very nice paper in 2014 that we published. So to conclude this talk, key points are that today's complex systems, including software-defined networking or cyber physical systems or smart grid or whatever, contain a huge amount of software, which has immediate implication that software becomes a major cause of system undependability. And software failures during operation, therefore, are a fact that we need to learn to deal with. And traditional methods of software fault tolerance during operation based on design diversity are found to be very expensive, hence do not get used extensively. Software fault tolerance based on what we call environmental diversity, which is relatively inexpensive, could be or should be exploited a lot more. And the focus of the software engineering community so far has been on software faults, how to find and fix bugs, which is fine. But we need to pay some attention, if not equal attention, to failures caused by software bugs or faults and the recovery from these failures during the operational phase. And focus of the software reliability engineering community has to move from not just Bohr bugs and software reliability to software availability and Mendel bugs as well. And so overall, we talked about to achieve highly reliable software fault avoidance, fault removal and by testing and debugging, and fault tolerance using design diversity and environmental diversity. And we can also talk about fault and failure forecasting, which I'm not going to talk about today. So some more notes. Conventional wisdom is that unlike hardware, software does not age. So preventive maintenance does not help in software. Well, since 1995, it has been recognized that software also ages, and this is a talk in itself, separate talk. And software rejuvenation, preventive maintenance in this context has been called software rejuvenation. And there is a monograph recently published on this topic that you might want to look at. So this talk has been drawn from many different references. Some references on the fault classification are given here. Some references on the environmental diversity and methods of mitigation are given here, and many more. And prediction of fault proneness modules is given here. And that concludes my talk. And I welcome any questions, comments, or any criticism. Fortunately, in this remote sense, people cannot throw eggs or tomatoes at the speaker if they don't like the talk. But I welcome questions. I know it is very different from the queuing talks that you heard earlier, but this is what I've been doing lately. I used to be doing queuing too, and a lot of reliability and availability modeling. But making software more reliable is a much more interesting problem, and I've been trying to do that for the last 10, 15 years. So I welcome any comments, criticism, questions, etc.
Okay. Включи звук. Thank you very much, Professor Trivedi. It was a very interesting message. A question, please. Professor Rykov, have questions?
No questions might mean talk is boring.
I'd like to ask about possibility to see your slides in the material of conference. Is it possible?
I can send the slides.
Is it possible to see your slides in the conference materials?
Okay, I will send them to the organizers.
That may be question to Wisniewski.
Yes, that will be very good. Yes, I will do that. Yes, sir. Any comments, questions?
Yeah, may I ask a question? This is Udo Krieger from the UNESCO
Hi, Udo, how are you?
Heritage Site of Bamberg. And thank you very much for a great talk. If it would be bad, they would send drones from Moscow. Don't worry, sir. If no drones appear in your site, Duke University, everything is fine.
All right.
When we see these days the application of self-optimization, self-healing, using data analytics, what is the role of this technology with respect to software? I remember we had in the NASA vehicles different items, and then they applied a system there.
Yeah, so the notion, the part I didn't talk about, which is software rejuvenation, is where this can be used. So basically, as time goes on, there are some bugs that memory leak is one principal example, but there are many other types of bugs like that. As time goes on, more and more memory will disappear into a black hole, and after some time, the system will slow down or might crash. So this is aging-related failure, it is called. And since it is possible to monitor system behavior, system resources, and try to predict when such aging-related failures might occur, it is possible then to do a preventive maintenance, which is called software rejuvenation. So software rejuvenation may be triggered based on simply time-based rejuvenation, or it can be based on inspection of the system resources. And if you should choose to inspect system resources, then it is possible to take this data and from that predict when the failure might occur. And this data analysis can be done by standard statistical time series methods or more ML or AI type methods. So all these methods can be applied and have been applied to try to predict when the aging is getting very bad, and that you should then rejuvenate the system. So that is one way of self-healing, yes.
Thank you. Thank you very much.
And there is a monograph now on this topic, as I told you, published last year, Software Aging and Rejuvenation, it's called.
Know that. Thank you.
Another question, please. No questions. Thank you very much, Professor Trevedi.
Thank you. Namaste. Or Vidasen. Udo, it's very nice to talk to you by these Teams. And I see the beard is there, huh? Professor Janos, very nice to see you also on.
Thank you, sir.
Dharma, very nice to see you. Who else do I know? I'm sure I know some other people, but I don't see their pictures.
Some of my students are here to listen your talk.
All right. So I hope I motivated some people to work on these Mendel bugs. There's a lot of work to do.
Thank you.
Okay.
Thank you to all.
Dear colleagues, we have finished the plenary meeting. Many thanks to all the participants. Thanks. Все, можно закрывать, да.
Hi, Evgeny. I'd like to see you and to say you several words. It's very nice to see you again. We did not see one another during long time.
Я надеюсь, мы еще поговорим.
Ну, я не знаю, как это осуществить. Вот если Вишневский не закроет быстро этот самый разговорник, то можно еще и поговорить. Janos, best to see you. Nice to see you again. And thanks for your presentation. It's very nice.
Спасибо, Мала. Спасибо, Владимир Васильевич.
Сегодня у меня с утра были лекции, поэтому я не смог присутствовать на вашем докладе, господин Левнер. Но надеюсь увидеть его в материалах.
Профессор, ты много потерял, да.
Ну, что сделаешь? Значит, я же не мог рисковать своей зарплатой ради бесплатного участия.
Давайте переходить на английский, потому что не все понимают русский язык, да.
Well, I cannot risk with my salary, and because I am professor of 2 universities, and today I have lectures one, and tomorrow I have lectures in another one, sorry. But I will present in the conference in Wednesday, where my talk will be presented also. Thanks to all for your participation.
So do you plan to give some lecture, Professor Rykov?
No, it will be short talk, 15 minutes. Professor Vishnevsky do not give me the possibility to give a long talk.
I'm very glad to see you.
Well, nice to see you too.
Thank you.
Thank you.
See, bye.
Bye-bye.
Bye-bye.
Bye. Bye.
Bye.
Okay. So, thank you, Professor Vishnevsky, for very nice organization. I am very much impressed by so many people and from all over the world. You organize almost all countries which we know doing in this area. Thank you. See you tomorrow.
Yeah, thank you, Evgeny. That is
Дорогой Женя,
because
я
our
надеюсь, мы
students
продолжим, так сказать, уже на русском.
are at the conference. Thank you very much for your presentation. Hello, that is Konstantin.
My pleasure. My pleasure.
And see you. Thank you very much.
Next, we'll be happy to meet you next time. See you tomorrow. Bye-bye.
Bye. Все, ребят.